Yeah.
You're now live. So yeah, you put that in your pocket or whatever. Don't worry so much about it.
So are we live? I think we're live. Are we live? We might be live. Okay. So welcome to day 2 of EXAG. We're just going to kind of get going again, another session of talks. We have a session of talks, another coffee break, another session of talks. Lunch, we're going to do the same thing with lunch as we did the other day, so kind of pull together options, throw together a pile of money. I'll be very happy about it. And after that, we're going to go into actually giving a set of like demos. If you've been hacking, you have a chance to come up, show some of that. Even if you just have a side project and you've kind of been working on it for a while, it's a great opportunity to come, show it off while you're working on it, get some attention, get some maybe other people to help in with it, chip in ideas or actual code. And then, yeah, we'll kind of wrap up and end there. So we're going to start with our first talk, and I won't bother reading titles because other people can.
Hello. My name is Martin Cerny. I'm from Charles University in Prague. And I'm gonna speak about a little game I made that's called Sarah and Sally. And I did some experiments on how to create a good Sidekick AI for the game. So, like the very basic idea is that Sidekick AI is kind of hard. And so, like the worst thing, some of the worst experiences in gaming are around caring for a badly written Sidekick AI, where instead of helping you fight the evil guys, it just keeps falling off the ledges and killing himself and preventing you from completing the level. And so, like, the only good examples of Sidekick AI I stumbled upon are things that are very, very heavily scripted. So just people put in so much effort so that it works in almost all cases, and just very, very heavy scripting. And so I wanted to experiment with doing Sidekick AI without the heavy scripting and understand what the challenge is and what are the problems. And so my first idea was that I want to design a game where you get rid of most of the difficult problems, like inferring what the player is trying to do. So just design around most of the problems and try to create a game where the actual AI part is relatively easy. And I also wanted to, since if I can create an AI that easily create an AI that performs well, I wanted to explore the experience, the player's experience, when he's cooperating with an AI that's actually good at the game. So instead of babysitting the AI, it's slightly kind of like the AI may be babysitting the player a little, or just, more of an equal partnership. And a small spoiler alert, I failed. But I'm gonna speak about the things that work well and things that didn't. And like the biggest success is that I managed to have this in time for AIIDE, which was a great experience. I recommend it if there's going to be AIIDE next year, so I strongly recommend it. So my biggest success was joining AIIDE and finishing the thing and doing something. So I'm going to show you how the game looks so that you have an idea what I did, and then I'll talk you through the motivation behind some of these things I experimented with. So the game is a puzzle platformer. You have 2 characters. The small one, that's Sally. She's controlled by the player. This is Sarah. This is Sarah. She's controlled by the player. The tall girl is Sally. She's controlled by AI. And as in most typical puzzle platformers, you're trying to get both of your characters to a correct exit of the level. And here, like it's turn-based. The first thing is turn-based, so that the characters cannot play at the same time. So it's either the player taking turn or the AI taking turn. The first mechanic is keys and barriers, so you pick up a key, barrier disappears. Second important mechanic is that Sally, the tall AI character, can help the player by levitating him with magic, which looks about like this. And then there are these special levers that when you use them, it rotates the gravity in the level and changes the direction. Yeah, which then lets you finish the game. And so, like, I try to keep the number of mechanics minimal so that I can do a simple game that people learn relatively quickly. The gravity rotation sync is useful because it tends to be hard for people to, kind of hurts your head slightly before you start to understanding it. But the for AI is just a different action. So that's kind of a sync where the AI has a slight advantage over humans because it just doesn't need to work with preconceptions about gravity. And also this enforces that the AI is helpful because it can literally do something that helps the player because there's no jumping mechanic, so the player cannot get up without the help of the AI. As you may have noticed, I tried to mask this a little, but it's completely grid-based. It's just really a grid of tiles. And when you're falling, you cannot change the direction of your fall. You just fall straight down. It's completely deterministic. So this makes this, from an AI perspective, a very simple world. Although I hope I managed to hide some of these things from the player. So it looks more or less continuous, but it's actually a discrete, completely deterministic thing. And so since I have this grid-based world that's completely deterministic, so I can use a very simple search-based AI to solve the puzzle. So it's just heuristic forward search with really just a few simple tricks to prune the space a little. And the search space is pretty small. It's like some 10 million in theory, and in practice, I never expand more than several thousand nodes, so it just runs super quick, although the implementation is shitty. And the nice part is that since this is a cooperation problem, I solve it actually as a single-player game. So I assume that I'll find the shortest path to exit for both of the characters, and I assume that the player finds the same or very similar solution to the level and just follows through. And the nice part about using search for this kind of thing is that the tree itself is an interesting source of information about the state of the game and something that you can communicate to the player and explain your choices a little. So some of the simple things I work with is that, for example, I may realize that the solution contains no actions of the AI. So I can tell the player, hey, I'm not doing anything because you can finish this by yourself. Yeah? Actually, that's the most important thing to communicate. When the AI does nothing, it's very easy to look stupid. So that turned out to be an important thing to communicate. The other part is that it may turn out that I have no reasonable action available unless the player does something, picks a key or something. Or the shortest solution contains, although I have some actions available, then the shortest solution requires me to don't do anything right now and give initiative back to the player. So that's some other thing I try to tell the player. And also I tell him I can follow how the game progresses. So I see, okay, so now my solution cost is now bigger than it was last time I was making decisions. So this means that the player did something suboptimal. He didn't choose the optimal actions. So I can tell it to him, just to be mean a little. Or even I can tell him that he just made the level unsolvable. And the nice part is that since it's fully deterministic, then the AI can never screw up, which is also another design decision that makes the AI that tries to make the AI appear intelligent. So the AI can never screw up. Only the player can screw up. There were some tricky things to get working. So one of these interesting problems I worked with was the cost function for the search. So, for example, initially I gave a high cost to the action that ends turn, that gives initiative to the other character. And the reasoning is was that I don't want like the player to, I don't want the AI to switch frequently, and so I want it like to complete with as few switches as possible because the switches seem to be annoying to the player. But the problem with high cost for ending a turn means that the AI tends to do some work for the player even if it's not very reasonable. So it would go like over all the map just to fetch a key that's on the next tile as the player is. So, and but when it was too low, then like the gameplay got a little fragmented, and the AI became less helpful. So because it ended up often doing no action, and just, you know, so you do it, you can do this. And so part of the solution was in sculpting the search space. So I have a simple heuristic that just says that the end turn action is available only when it makes sense, so only when I really did something before ending the turn. And so this is less of a problem because I cannot do it anytime. And what I ended up doing was that I only incur some cost for the end of the turn when there is a no-op. So only so I'm trying to minimize the amount of situations where either the player or the AI doesn't do anything. And well, which once again turns up a problem. I mean, what should this cost be for the no-op operation? And so if it was high, then the AI started doing stupid things just to avoid the no-op. And so it would often levitate the player, because the levitate action, it cannot really hurt the player. It cannot really do anything wrong. So it started doing like, you know, just levitating the player all the time just to avoid not doing anything. But if the cost was too low, then once again, like you would get a lot of no-ops from the AI, which wasn't kind of the experience I was aiming for. So in the end, I made the no-op cost high, but smaller than the cost of levitating, and so which kind of worked for this very particular situation. And as I mentioned, like since the search space looks the way it does, and the end turn is not considered often, so it's less of an issue. But generally, I think there's this is like a problem you would face in many similar applications. So you need to balance the cost function. There are some non-trivial things that they are not visible on the first side that you need to, even with such a simple game and simple AI approach, you need to tune to it work well. Another thing was that there are situations that are much harder to communicate than things like I need your help. And some of them is when the player does not understand me. He has a different plan than I do. And so because I don't model the player, I just assume him to be as optimal as I am. So I did a simple heuristic. So if 2 times in a row the AI doesn't do anything and the cost function doesn't decrease, then this means that the player wants me to do something else. So I levitate him, because that's like almost every time he wants me to do something, it's levitating. So, and this kind of worked pretty well. It also works pretty well because the levels tend to have only a single solution, or there are not so many solutions. So it very quickly converges that we do the same thing, because even if the player chooses a different path, that very quickly, like the path he starts to choose starts to be the shortest solution. So it's level design kind of helps in a way. And another thing is that if there is no solution, then like if I insist that there's no solution and the player doesn't see it, he believes, but I mean I can do this and then I do this and then I do this and I'll get to the goal. So the AI would seem stupid. So even though the AI knows there's no solution, it tries to get to a state that has the lowest heuristic value. And so, which again lets the player progress through game and then realize, oh, right now, yeah, I'm stuck, I cannot do this, and restart the level and start again. And if there's no other option, then I just do random action because there's no solution anyway, so I can do anything because it just doesn't matter. So during the development, I learned a few things. So the first thing is that puzzle design is hard. So there were a lot of like small things that were difficult to design right so that they don't distract players from the AI. Like I did some compromises to have the AI simple. So for example, I wanted the levitation mechanic to work only when the levitation beam between the characters doesn't cross the level geometry. But that turned out to be pain to combine with the search, so I just didn't do it. And you can levitate the player anywhere. The AI can levitate the player anywhere. I also had to implement all mechanics twice, basically, because you need to implement the search model, and then you need to implement the actual game, the animations, these kind of things. So that's like really frustrating, even for a small game, and for larger games, that would probably be more of an issue. We spoke about the cost function, which is a tricky thing, and that like this, I really like the idea of examining the search tree and explaining the AI choices in terms of the search tree. So this, I think that's applicable to a lot of other things. And then I did science, because this is a scientific conference. So I put the game online, and I let you can play it as well, and there's going to be a demo of it. So, and I picked 3 levels towards the end of the game, and I did a simple manipulation that in one of the levels chosen randomly, the player would control both characters. And then I put up a simple questionnaire asking the people if they had fun, if it was difficult, and if the AI was intelligent or if they liked it, and very simple few questions, just that people quickly select a few checkboxes. And I even asked the player if they felt better to control both characters. I had reasonable amount of participants, but since only like a third of them actually, for any given level, only a third of the players actually played with both characters, because one of the 3 was in random. So the sample size for the baseline, when they control the both characters, is pretty small, so the conclusions are kind of waggy. Well, results. The players really liked the AI. So like 88% of players agreed that it's intelligent. 95% thought it was helpful. 82% thought it was likable. They considered it not lazy for the most part. And a lot of the players said they did not prefer controlling both characters, although that's 55%, so that's not a huge margin, but still. But, a big but, they had less fun. So when people controlled both characters, they reported 95% of the player agreed they had fun, but when they controlled only single character, that it was 83. So the difference is not statistically significant, but I clearly failed to demonstrate that it's more fun playing with AI along. This is a breakdown by levels, and so you see that the co-op AI means I play along with AI, baseline is I control both characters. And you clearly see that here is just better than with the AI. The only slight difference is in the last level, which was the most difficult one, where it seems that the AI turned out better, but like the sample size, this is like 6 people, yeah. So that's like just that's very not so important. How much time do I have? 3 minutes, okay. So I have some qualitative feedback as well, not a lot of it, but it was fun. So for example, like players thought that the player reported that he saw that he doesn't like to control the other character. And then he did try controlling the other character, and then when he turned back to the AI played, it became more annoying to him. So that was a nice comment, I just like that. So, and it means I did my character design well. And that's another nice part. And when Sally told me we cannot win, I thought she was just kidding, and I was trying to finish anyway. So that shows that it's important to really prove to the player that it's not possible. This is another thing that I dislike, that Sally prioritizes getting to exit herself over helping. And obviously, like the exit, reaching exit is a special action, because if you reach the exit first, then you're kind of selfish. Yeah, but if you like pick a key first, then although you do fewer things, it doesn't appear too selfish. So I think that's like just maybe cost function could be tweaked a little to avoid these kind of things. But I don't know. Yeah, and the other thing is which I think is important, that the player didn't like that he was immediately told that there's no solution to the level, that he screwed up. And I think that's kind of one of the things that I could say in general, that the AI, that I wanted to make sure the player understand the game, that they know how to play it. And so the levels were quite easy. And maybe then with AI helping you, they became just too easy. And so maybe this would have worked better if I had levels of more complexity where really solving them on your own would be difficult, and you really needed a lot of help to the AI, and still like understanding the AI and doing the things would be challenging. So maybe that would help. Also, that's a similar note that there's need to balance the helpfulness of the sidekick. So if he's too active and too effective, just too good at playing the game, it may ruin the fun. You may like him, he's okay, he's fun to be around, but I cannot play the game myself, I don't have my time to solve problems. And so that's maybe if I had more challenging levels, it would have worked better. And also there's a lot of research on user perception of computer personalities, which I didn't use because I didn't know about it, and was pointed to me by a reviewer. So there's just one small thing that I have to put it in the words of classic. So literature research is very important. So, but well, this was just a small project, so hell. And I think there's a take-home message here, and that's that even though you can make your sidekick intelligent, you can make it perform well, you still have a lot of problems you need to deal with, design-wise and from other perspectives. So just having a good AI algorithm will not get you that far, as we've seen in this case. Okay, questions? Yeah, it's every time the AI gets to move, it just searches. It's super quick, so I mean, it was the simplest way to do this.
So you only looked at, when you were evaluating the results, you only looked at what players responded.
Yeah.
You didn't look at the gameplay traces.
No, I didn't have those, like for technical reasons.
Okay.
I know whether they. I didn't even have questionnaires from people that didn't complete the level because I cannot detect that. It was like a very simple setup, so.
But it might actually help to know which parts, like when they say they have fun, did they actually like traverse more of the level and things like that?
Yeah,
what Sally did.
Yeah, that would obviously be interesting, but I don't have the data.
Sure.
Okay, yes, please.
I think I understood that you yourself designed the puzzle levels, is that right?
Yeah.
And the way you described them, it sounds like almost you don't actually need an AI to solve them, like you already know the solution. And so you built one that solved it anyways, but it's almost like there's a closed form solution, and maybe the people had a different experience than they would have if it was a situation where the AI can make mistakes and be like a real AI as opposed to really a closed form solution that just happens to get solved every move. Do you have any thoughts about that? Or it's almost like you're tricking them into thinking there's an AI when there's not, because you don't need an AI in this case. Does that make sense?
Yeah, so like it's not like maybe it's not pre-computed. Like, some of the levels have variety so that it wouldn't be practical to like store the solution and pre-compute it. So it reacts to the player in a way, like not a lot, but it does. So that's one thing. And well, I mean, I was trying to explore just the design space where the AI doesn't make mistakes, because I noticed that a lot of people just post these videos. Like Daikatana was famous for it. Like you had really just to babysit the AI, and it was a lot of pain. So I was trying to explore like the very opposite, where the AI makes no mistakes, and see how that works. So I mean, obviously, like you would want the AI not to be perfect in most games, but I think it was just an exploration of what happens when AI is perfect, basically. Yes, please.
So kind of feed it from Dan's question, because I have the same kind of idea. If you're doing a sidekick AI, it is different than making a super optimal, parent AI, let's say.
Yeah.
So you're trying to make it be, you're the hero and it's the sidekick. The relationship is different. So having it do dumb things and having it take suboptimal routes. It's like, it's kind of the semantics of what you call sidekick AI. So I think it's important to have some sort of non-optimal, or at least like random, dumb.
Yeah, I think it's related to like my second goal, like explore the design space where really the AI is not subordinate to you. Yeah, because really in the game you like the AI needs you to do things. There are things that like the AI cannot solve it on its own, but also you heavily need the AI to help you solve the levels. So I think there's some interesting design space around here as well. So it's more like, yeah, it's actually partner AI and more like it's not exactly sidekick in the typical sense. That's right.
Any more questions? All right, let's thank our speaker.
Yeah. Oh, one more thing. I just did one slide. I just wanted to show you. I put that out because I had too much slides. But you should play Dearth. That's a good game. And it's about. Actually it's one of the things I found out after I made my game, that I found out there's a nice game called Dearth, which is based around a similar idea, but it's real time. You can photo the slide or just it's linked in the paper as well. So it's an interesting game that explores MDP in a similar way I work with search and explore cooperation with AI, and it's a different concept and very nice, very well done. So one last thing, okay.
We should hook you in. Yeah, are you okay for me to stream the talk?
I can speak or I could use the mic. Yeah. Which do you prefer?
This is just for the
Oh,
live
for
stream. Are you
recording.
okay for?
I'm totally.
Yeah.
That's fine.
Perfect.
Sounds like a professional with all this stuff.
Like a professional, but not actually one.
Well, we're not paid
That's
for it,
basic.
you're not professional.
I don't know.
No, there's other things. Trust me. Yeah, just generally screw things
I
up.
can give you a couple dollars for it.
Okay.
You can do that.
Yeah.
Then you
If
can
you're
say
up
you're a professional. Yeah.
You can basically put this onto your badge. Doesn't matter where it is really.
Okay.
It'll pick it up and then just
Just
shove
kind of
that in your
around.
pocket.
So, you all mic'd up? You good to go?
I'm about to.
About to be. In the meantime, continuing our character theme with another paper on virtual characters from a very different angle. So it'll be interesting to see how James is approaching this. I'll leave it to you.
Okay. Do you want to do a mic check, or are we just assuming it's good?
I'm sure it's good.
Okay. Can everyone see this? I don't want to block anyone's view. This is a really visual presentation. Okay, so this, my name's James Ryan. This was joint work with Adam Summerville over here, as well as Michael Matthias and Noah Wardrop-Fruin. We're all just a couple floors above here at the Expressive Intelligence Studio here at UC Santa Cruz. So toward characters who observe, tell, misremember, and lie. By observe, we mean characters in game worlds who actively perceive those worlds, building up knowledge of them as gameplay proceeds. By tell, we mean characters who take their knowledge of the world and tell it to other characters who may propagate it further, yielding rich knowledge networks and characters with rich knowledge. By misremember, we mean characters whose knowledge of the world may deteriorate or be altogether forgotten. And by lie, we mean characters who tell not what they truly believe about the world, but lies about the world as acts of deception. So I'm going to assume we want to see these things in games. The people that were part of this project, I'm just going to assume I'm speaking to the choir here, skip problem formulation and jump straight into the technical nitty-gritty. So in this paper, we present an AI framework that supports characters who observe, tell, misremember, and lie. And because we believe, it supports many characters who do this at once, actually very many characters doing this. So we're targeting about 300 to 400 characters engaging in this knowledge phenomena in a simulation at one time. Now, because we believe that AI frameworks that are meant to afford playable experiences that are totally new should be evaluated through those very playable experiences, we present our our AI framework in this paper through the context of a particular playable experience called Talk of the Town. So I'm going to spend the beginning of the talk giving a brief overview of this game, which we have not developed yet, before proceeding to talk about the AI framework, which is totally complete. When I do talk about the AI framework, giving examples of characters observing, telling, misremembering, and lying, I'll be doing it in the context and particular domain of Talk of the Town. So it's important that I talk about this game a bit first, even though it's not made yet. So Talk of the Town is a dwarf-like, meaning a game in the mold of Dwarf Fortress. And like that game, our game has a world generation procedure that precedes gameplay. So our world gen procedure always starts in 1839 with an empty American townscape. There's going to be a couple families who decide to build farms in the town, build homes near the farms, move into those homes, and then set up a couple roadways between the farms. So we're going to call this example town here EXAG, which here in 1839 has a population of 11, as you can see on the bottom. So a couple years are going to go by, the world generation procedure proceeds, and you notice the population's grown a little bit. Maybe a couple of the families had more kids. But let's say in 1843 here, someone's going to move from outside the simulation to start a business in town. So this could be a general store, a horse stable, blacksmith shop. We have a sort of small knowledge base that we've authored of which types of businesses are appropriate for which American historical eras. So this person came from outside the simulation, built this business. They're going to want to live here too, the population increments. And we're going to jump ahead now a couple decades. So you see a couple more farms have been set up. We have several more houses, a sort of small business, industrial areas emerging around that first business. And everything here is happening by utility-based action selection. I'll give an example of this in a particular context in a couple slides. But basically, people are deciding what to do by scoring the utility of all potential choices. And a bunch of characters doing this simultaneously, very many times over the course of 100 years of game time yields these rich topologies, both in the physical city topology and also in social topologies and family networks that emerge. So I'm going to jump ahead now to 1888. The population is booming here. We can see a couple of neighborhoods. There's kind of different sides of towns that are emerging, and then a recognizable downtown area in the middle. So that's just the utility of where you want to start a business, depends on where other businesses are, in a way that makes downtowns reliably emerge. So now we're in the 20th century here. It's 1907. We can see the town is really starting to fill up. Our population is 211, and these farms are going to, at this point, start giving way to just homes and also to things like parks, and the homes themselves will start giving way to apartment complexes. So that's just more hand authoring, where we kind of goose the simulation to be era appropriate, so apartment complexes emerges when they should, and especially when population density is getting, as it increases. So let's say that we have some character in the simulation here who grew up in EXAG, his parents grew up in EXAG, his grandparents grew up in EXAG. Let's say he's a great-grandchild of one of those original farmers that started this town. So he grew up in the town, he knows many of the people who live here, and he's now like 19, 20 years old. He works at some bar in town, and he wants to move out of his parents' house and build his own house. So he's going to score all of the open lots in EXAG for the utility with regard to a number of social concerns. So depending on his personality model, he might want to live by his family members, in which case he would score lots more highly if they're near where family members live. If he had a different personality model, he might want to live away from family on the other side of town, so he would inversely score those lots. Certainly he's going to want to live by the bar that he works at. He's going to want to live by maybe his favorite restaurant, his friends, things like that. So a number of social concerns, all affecting the utility of potential choices, in this case, potential lots to build a home on. So he scores all of them, and then he's going to pick the largest one here. Actually, it fits a probability distribution to the utility distribution more accurately. But let's say he picks this one with the 19 here. He's going to build a house here and move in. So that's an example of utility-based action selection. It's happening in a number of different contexts. We just obviously hand-authored the utility scoring procedure. But just a bunch of characters doing this causes these cool topologies to emerge, like downtown areas, but also things where, like, oh, the south side of the town is these couple families, north side is people that work downtown, things like that. So there's sort of a social topology that rides atop of the city topology, but actually is like reified in the city topology itself. So now I'm going to jump all the way to 1979, and this is when gameplay in Talk of the Town takes place. So we see the cityscape is really filled up, that downtown area is just booming, a bunch of apartment complexes, and then we have this kind of anti-downtown area to the south where people didn't want to have their business by downtown, but then there's kind of feedback happening there where more businesses then open. So maybe in several more years, the simulation won't progress any further than this, but you could have like a separate downtown. So we stopped the simulation in 1979, and then we rig it such that the story surrounding gameplay in Talk of the Town always emerges. And the story surrounds a very old character who's very rich, who has many family members in town who are waiting for their inheritance. Now, on their deathbed, this character at the last moment signed a document willing everything to a secret lover. So the family members did not know about this secret lover, and they still do not at this point. So in 1 week, there will be the lawyer of this character will read their will. And if they just read the will as it was written, the family members will get all the money. But there's this lover character with this lover document. And if they're able to deliver said document to the lawyer at this will ceremony, then the lover gets all the money and the family gets none. So meanwhile, the family is sort of hearing rumors about this lover and this document, so they're trying to figure out who this person is. So that they might just kind of apprehend them, bump into them, and make this document go away. So the game is an asymmetric multiplayer game. One player is the lover character, another player is a member of the family. And the member of the family is just trying to figure out who this person is, and this lover is just trying to not be figured out. So in order to figure out who this person is, the family member who grew up in the town and knows people in the town as reified in the simulation itself must manage the knowledge network. So knowledge propagation is one of the major aspects of the simulation, as I'll spend most of the talk talking about. So they're trying to sort of manage this knowledge network such that information about the lover flows toward them. And the lover then is trying to pollute this knowledge network such that misinformation flows toward the other player. So that's Talk of the Town. It's early in development, I guess, but the simulation is the AI framework that I'm going to talk about now. And like I said, that's totally complete. We actually have a demo today, I'll talk about this at the end, that takes place in this simulation. So in our AI framework, characters build up knowledge of the world that is structured as an ontology. So if you dive into the mind of a character, you're going to find a series of mental models. So each of these mental models will pertain to some entity, either a business, home, or other character, and will be composed of a number of belief facets, each pertaining to a specific attribute of a character. So if you have a mental model about another person, it's going to have things like their name, their hair color, their occupation. If you had a mental model of a home, it's going to pertain to things like who lives there, its address, for a business, who works there, and its address. So we've so far authored 42 different belief facet types for beliefs about people. I think 25 of them pertain to physical attributes, because in Talk of the Town, a big thing is figuring out the appearance of this secret lover character. So appearance really matters in the simulation. For beliefs about homes, we have 6 belief facets currently, and for beliefs about businesses, we have 5. So I won't enumerate those. So this is a collection of mental models, which for a real character would be between like 200 and 500 mental models. This is obviously a simplified example. But I said earlier that this is an ontology. So let me explain how it is an ontology. So if you look at a mental model, most of these beliefs are going to ground out into things like strings or integers. But some of them, like a belief about where somebody works, will ground out into a pointer to that actual business that they work at. And more accurately, it'll ground out to a pointer of the person's mental model of that business. So we're in this person's mind. That's what the purple means. They have a mental model about a person. Their belief about that person's workplace will actually ground out into their belief about that very business that they believe they work at. So in this way, it's not just a collection of mental models, but an ontology of interlinked mental models where each linking has a semantics. So on the top, if this person believes these two people are married, then that link would have a semantics of is a spouse of. So to briefly recap, because this is important, people have knowledge in the world. If you look at it, it's going to be a series of mental models that are semantically interlinked. Each mental model pertains to some entity and is composed of a number of belief facets, each pertaining to specific features of the entity the mental model pertains to. Now, a core notion, or maybe the core notion in our system, is called evidence. So all this knowledge phenomena can be explained in terms of evidence. So we mean evidence very broadly, as you'll see here. So all beliefs that characters have will be supported by evidence, and in fact, it is in response to evidence that all beliefs are formed in the first place. So if a person has a mental model about, say, another character, all of these belief facets will be supported by pieces of evidence, and in fact will have been formed upon encountering an initial piece of evidence. So each piece of evidence has some metadata on it that's tracked by the system. Characters aren't reasoning about it currently, which is the time step it happened, basically where and when it happens, and the type of evidence. So we have an evidence typology with 9 types, and these 9 types work to explain all of the knowledge phenomena in our game. So I'm going to sort of go through each of these, and even though I'm just talking about like pieces of evidence, really I'm painting a larger picture of all the knowledge phenomena that happens in our system. And I'm going to only use examples of beliefs about other people. Keep in mind, people are forming beliefs about businesses and homes. I'm only going to do examples about other people because they're more interesting and just for the sake of example. So the first type of evidence happens when someone just knows something about themselves. So people just know the truth about themselves. We call this reflection. So if you look at a mental model that someone has of themselves, there's just going to be a bunch of reflection pieces of evidence. So this is pretty boring. People just know the truth about themselves. We're not doing anything interesting here. One thing we could do that would be interesting is that we are modeling the effective age on memory. So we have a memory parameter in a person's representation. So we could actually do interesting things where people are like forgetting their life. I could see a whole game about that. But we're not doing that currently. We could. The next type of evidence happens when someone observes someone else. So this is the crucial type of evidence when 2 people, I failed to mention that we have a day-night time step. So each day has 2 time steps, day and night. On every time step, someone will be somewhere in the city, either where they work, at a bar, at a friend's house, at home. They'll be someplace in the city. So everyone is at someplace, they stay there the whole day. During the night, they'll go somewhere else and they stay there the whole night. So let's say this is a bar in town and we have 2 characters that are both here at once. These characters might observe one another. So we call this type of evidence observation. It's like the core thing in our game. It's how almost all knowledge is formed. So whether or not some character observes another character will depend on the latter's salience to the former. So I have a whole paragraph on salience computation in the paper, but basically things like, is this my friend? If they are, how good of friends are we? Am I romantically attracted to this person? Is this person a coworker? Is this person my boss? Are they a family member? All these sort of social concerns are feeding into how salient someone is, and how salient someone is affects how likely you are to observe them. So there could be 20, 30 people at a place at once. You're not going to observe everyone. You'll observe people probabilistically according to their salience to you. Salience is not bidirectional. It's not symmetric. So let's say that this character observes this character on the right, and they did not have a mental model of them yet. They're going to instantiate a new mental model and fill it up with some initial belief facets. So when you observe someone, you don't just fill all 42 belief facets. You fill them in probabilistically according to the salience of each facet. So we basically author things like expressing that hair color is more salient than like the shape of someone's nose. And then all of these new belief facets will be supported by an observation piece of evidence, which is like at this bar at this time, an observation happened where this person saw this person. But let's say this person observes this person and already had a mental model of them. They just might observe new things that they missed before and support them with an observation piece of evidence here. The next type of evidence is almost as crucial, and it happens when people tell things to other people. We call this a statement. So 2 people are at this bar again at the same time. One of them might initiate a conversation with the other one. Whether someone initiates a conversation depends again on the salience of that person, but more importantly on the personality model of the potential initiator. So their extroversion component is really big there. If they're good friends, they're more likely, things like that. Or all these social concerns are feeding in. It's utility-based action selection again. Okay. And when people do talk, they'll talk back and forth. And they'll talk about a number of subjects of conversation. So here the system's going to take everyone that they both know about, score them for their salience with regard to both people. So the sum of this prospective subject of conversation salience to both characters. And then retain the top n to be subjects of conversation, where n depends on how good of friends these 2 are and their personality components, especially extroversion again. And they're just going to rally through these one by one. So it's not a very realistic conversation. It's just a passing of information, essentially. Now, when they talk about a particular person, they'll each pull up their mental models and then take turns talking about them. Each time someone talks about someone in their turn, they'll bring up a particular belief that they have and say the blue character does not have this belief already if we actually line these up line by line. So they're just going to instantiate a new belief. This is their first piece of evidence for that. They're just going to accept it, and they'll give a statement piece of evidence to that. But let's say blue said something about this character that purple already had a belief for. Well, now it's crucially going to depend is this whether or not this new information supports the belief they've already had, in which case they'll just put this as new evidence further supporting it, or if it does not agree with the belief, then they have to enact a belief revision procedure, which I don't have time to talk about here. There's a long paragraph in the paper about that. I'm happy to talk about it offline. It's one of the cooler aspects. I just don't have time to get into it. Basically, it's does the strength of this new evidence outweigh the strength of my belief? If it doesn't, keep my belief and remember it for later in case other people keep telling me about it, and the strength of that candidate belief will, once it passes a threshold, I might adopt it. So I guess I did just explain it, basically. The next type of knowledge phenomena could be really cool. It's not that cool in our system. It happens when someone does not tell something they actually believe about the world, but instead a lie about the world. We call this a lie. So we actually have a specific definition of a lie, which is that it doesn't matter if the thing is actually true in the ground truth of the world. It matters if the liar believes it or not. If they don't believe it, that's a lie. So just like people take turns talking, delivering statements during conversation, someone might just throw a lie in there. And it's not interesting because it's happening probabilistically right now, basically according to the personality model of the potential liar and their affinity toward this character. The less affinity they have, the more likely they are to lie. But I've been looking at a lot of social science stuff that could be operationalized on lying, so it could get interesting soon. Just to ground out this definition, I'm going to skip this actually because I'm a little low on time. Right? Basically, if this person believed this person had brown hair, if they said to them they had brown hair, that would not be a lie, but if they said blonde hair, that would be a lie because they don't believe it, even if blue has blonde hair. So it's not about the ground truth. When people hear lies, they just think they're statements, and the system will attach a piece of lie evidence, so the system always knows the truth, but they'll reason about it like a statement. The next thing happens when people are talking and someone else overhears. We call this an eavesdropping. They can overhear lies or statements, and basically they become this sort of external recipient where their piece of evidence is according to the system an eavesdropping, but they see it as a statement, and it might be a lie, actually. Now, the next type of belief phenomenon happens when someone just makes up something out of thin air unknowingly. So we call this confabulation, and basically just like out of the ether, some belief just enters their mind. So we've all experienced this, right? Confabulation. And the belief they confabulate will be according to the distribution of features in the town. So if you're going to confabulate a belief about someone's hair color and 70% of the town has brown hair, you'll have a 70% chance of confabulating brown hair. So it's sort of this Bayesian thing, but like cheating. The next type happens when two people remind you of each other. So this green just reminds this person of blue. And so they might take a belief that they actually hold about green and unknowingly inject it into their mental model about blue. We call this transference. The next thing, which is actually pretty foundational too, happens when you have some belief and it mutates. And of course, this is all unknowing. The system's tracking everything, but the characters don't know this is happening. The strength of their beliefs will decrease when these things happen, but they won't realize that it happened. So this is called mutation, and something that might mutate is like hair color going from brown to black. So here there's quite a bit of authorial burden to specify how things should mutate, so that brown's not going to like 33, which would be an age belief and things like that. So we specify basically like state change probabilities. So here there's a 75% chance of mutating to black, this much to gray and white, and so forth. And the last type of belief is how beliefs die, and this is when someone simply forgets something, and we call this a forgetting. This is happening probabilistically according to a configuration file that we authored. So we have these 9 types of evidence that sort of give you this broad picture of all the types of knowledge phenomena. And you can see that I mean evidence in a broad sense. You wouldn't consider like a forgetting a type of evidence. It's evidence for the system to be able to reconstruct true trajectories of all knowledge. So the system could visualize that like this character just confabulated this thing and then told it as a statement and it spread across, and then this person, it mutated in their mind, and that became this crucial thing where they found out who the lover was, or didn't because of that, I guess. And the system could just visualize all that after. So we really wanted to maintain evidence about everything. So we have reflection, observation, statement, lie, eavesdropping, confabulation, transference, mutation, and forgetting. So to briefly conclude, we have this system where characters may observe, tell, misremember, and lie. And I've told it to you in the context of this particular playable experience. But the system, though you have to author a lot to get it into a new domain, is domain agnostic. So it could be used in other domains. We have a demo today that takes place in this simulation, except that Ben Samuel, who's an actor in our lab, acts out every NPC by being fed the knowledge that they have by a secret interface, which is not so secret, I guess, if you play now. So we have this demo. It's going to be today. It's called Bad News. I won't give too much away. Thank you, by the way. But it's going to be today, 2 to 6. We're having people sign up for time slots because it takes 15 minutes to play, 20 minutes with like us telling you how to play. So just like approach me or Adam Summerville if you want to sign up. We have a sign up sheet. We'd love for you guys to play. Thank you. Yeah.
This is absolutely great.
Thank you. Thank you.
This is super, super exciting.
Thanks, man.
Do you think you will ever want to do like second-order reasoning where people suspect someone is lying, or they
Absolutely.
if someone is lying? Okay.
Yeah.
And is this like an exponentially more complex thing, or?
No, it's just reasoning when you, then they won't just treat everything as statements. When someone presents a piece of evidence to you, you'd have to reason about that piece of evidence. It's not, there's no like blow up problem. It's just like a handcrafted AI reasoning problem where you'd have to get interesting reasoning about like, why would this person lie to me, things like that. It's not even like a search problem.
Also, did I mishear at the start? Is Talk of the Town single player, but you're searching for a specific second player?
Asymmetric multiplayer.
Right.
Yep, so each player is, there's 2 humans playing the 2.
That was what I thought. That's even more interesting. Yeah.
Okay, cool, yeah. Bad News is single player, but Bad News is like an early demo in the shape of Talk of the Town. Yep.
So there seems to be a lot of ways that false information is injected into the system.
Yep.
So I was just wondering, I don't have any notion of how far along any of this is, but like, is it actually possible to learn the truth? Or sort of how often do you sort of learn lies? Like how often does the truth win?
So those are like tunable parameters. We had too much mutation going on at times for certain things. Like we still haven't fixed, people just can't remember addresses of like where their mom lives and just give ridiculous addresses. So addresses mutate by mutating the street or the block or even the address. And if all 3 mutate, it's just like this side of town instead of where their mom actually lives. So mutation has gone out of control at times, but we can just turn it all down. It's easier than you'd think, I guess, by all like the misinformation I've presented.
We've had some interesting experiences where, like, one time, like, I was playing the game that you hopefully will play later on today, and like, the person was like, "Oh yeah, I know exactly where the person you're looking for is. So you just need to go to this address." I went there, and it was just an empty lot.
Like no street even. Like.
Nothing ever existed there. Nothing ever existed there.
Yeah.
The guy just,
Yeah. The guy did know at one point, but it mutated. But yeah, there's more true information than you might think.
Okay, cool.
I think here was first, and then. Yep, go ahead.
So is the probability of mutation weighted by like how well someone actually knows someone?
Yeah.
Or is it all just
Yeah, it's weighted by the strength of the belief. The strength of the belief will depend on how well you know someone, because if you know someone better, you'll see them more often and then build more beliefs, right?
Okay.
People don't just automatically know things about people they know. They have to actually see them. But because they know them, they'll see them more. It depends on the strength of the belief and also the salience of the type. So you're more likely to forget someone's shape of their nose than their hair color, going back to like the notion of salience there.
Yeah, I just wanted to comment. It's really interesting work.
Thanks.
I'm, as usual, concerned with authorial burden. And
Yeah.
more importantly, like tuning these parameters that you mentioned,
Mhm.
that's going to be kind of.
Yeah, like it's a visualization problem because you have to be able to visualize
Well,
how it's working to you.
Because that's quite low. You know.
Yeah.
It can go wrong.
Yeah, we're more optimistic than you might be from having play tested. Yeah,
Sure.
from having play tested actually. So I guess optimism is not even the word there. Yeah, it was a little easier to tune than we thought because we were worried too. Yeah. Yep.
So, this is a question about if people will like this game. I think hear me out.
Yeah.
I think it's amazing what you've done to sort of, I mean, all the complexity there is really fantastic.
Thanks.
All kinds of cool stuff you do with it. But it seems to me almost like Clue. Well,
Yep.
Except that if you win, it's as lucky as not, right? Like in Clue, if you're smart, you just know when you're right because you've eliminated all the other possibilities and you know what the situation is. Here, there's all this confabulation and phony baloney stuff going on, and you could stumble into finding the lover or not.
So,
and
okay.
It's like you almost don't have the control to know if you're going to.
So you get control in the sense that you're not just like you're not at the behest of a single person's belief that they tell you. You can like cross-validate with other people's beliefs, and you might realize that this person like tends to forget because memory's modeled, or you might realize that this person's lying because everyone else is telling me something else and they're telling me this. So because there's 300 or 400 people in a town at any point, you're not as, you won't play victim to false information as often as you'd think, because there's going to be more true information out there, and you can just do your due diligence in actually backing up things that you find out. But like whether it will be fun is still sort of a remaining thing. Bad news is fun, I think. Yeah. Yeah.
To what extent, if any, do the player characters store any of this similar state that the NPCs have, right? Because like, or is it just I am the entire state of the player?
So one thing we've struggled with totally in this is if the character is born in the simulation and grew up in it, how do you express that knowledge to the character? And then how do you like make the character beholden to actually playing themselves correctly? And we've just struggled with that. And in bad news, we don't do that. You come from outside of the simulation. And so you're just yourself doing actual real knowledge phenomenon.
Because here it seems like it may not matter, but if you were doing, say, an RPG, I might want to know whether I know that guy's name. And so like,
Yeah.
it's really fuzzy fast.
Yeah, it's tough because it's, again, a visualization problem, a different one there. And like, how do you express that? There's not really games where you have a really rich character history that's like, rich in the sense of super multifaceted. I saw some hands. Peter?
Second order mental models, have you thought about them? Are they
Yeah, so that's like super easy, and that's my next step. As part of my, this is sort of foundational to my dissertation work, and these mental models can completely be recursive given the architecture. You can easily do theory of mind by just forming a mental model of someone else's mental model. And it's like the same object, it's the same class in my Python code, it's just recursive.
But I mean, in terms of computational complexity, do you think that there's going to be a barrier or not?
No, I don't think there's much blow up there. There is like speed issues already. I don't think that's gonna like blow it up. It'll make it more slow, of course. Yeah. By the way, this code, I think I'm fine with sharing it, and I would have to talk to Adam too. But if people are interested in this, it's on GitHub. It's Python code. Jim.
I guess related question, is there now some notion of reputation or plans to add some notion of reputation into the system? You know, like if I've just talked to someone and I know that their hair is blonde and somebody else is telling me their hair is black, like I'm gonna start saying like
Right.
this person has a bad reputation and I'm just generally not gonna believe what they say.
So there's a notion, there's affinity, which is like maybe a catch-all, maybe a superset of reputation. And when someone figures out, actually this isn't implemented yet, but I have like a total plan where someone figures out that information that they were told is false, they'll drop their affinity toward them. And then there is a notion of trust that I haven't fully implemented yet. And so that would be the sense of reputation you mean, right? Like, do you trust knowledge that they would be telling you? Yeah, so there's plans basically, but it's not quite there yet. It's basically people constantly updating their trust of someone else based on like verifying whether that information was true. And then the player, of course, is doing this in their mind with their brain. But
so after mutation, does it reach stable points if you just leave it alone and without the player interacting, just the characters talking?
So these kind of topologies do reliably emerge of like downtown areas and things like that. That's sort of a.
Because of the knowledge people have, like, does everyone learn everything about everyone else, or the lies take over?
It depends how much time you go ahead, right? So like people will move into the simulation and you don't know anything about them. And then, so there's always sort of like new elements being injected, and people are born all the time. So then there's new characters you never met, and you probably will meet them because it's like the son of your friend or something like that. And then that's a visualization thing that I can't visualize yet. So I don't know actually how to answer that truthfully. Yeah. Cool.
Thank you again.
Thanks.
Yeah, I'll just put it on. Don't worry.
Do you want the lights on or off? Because the camera's now
getting to know what everybody is doing. There's a plan for my entire thesis, and I'm going to make a UML of the entire process. Grows and grows and grows. Ship it in, write an introduction, and call it a statement. So if you can't put up everything on GitHub, you should at least offer it as a web service. And web services, which I'm going to demonstrate today, are really beneficial to you because you can make your research available without needing to comment it a lot. You'll still need to provide some sort of interface and documentation of that interface. You can decide which bits are accessible to others, and parts of them that are not ready yet, or you're too ashamed about, or you're planning on working more on secret projects, secret publications, you can keep secret. And you can run it anywhere, so it's a cloud service. You can run it on your phone, you can run it on somewhere that does not have a lot of computation, because the things that I'm going to show are quite computation heavy. The benefits to other researchers is that they don't have to read your code, they don't have to understand your comments or your spaghetti code. They don't have to download your very obscure IDEs, your Visual Studio from 5 billion years ago. That is the only thing that can run your code. And they can keep using their own, because we all do that. So they can basically integrate your stuff in their pipeline. There are obviously caveats, and that is, obviously you need to be online to use, as I found out today from my Wi-Fi at the hotel. If you have problems with connectivity, bandwidth is going to be an issue. Response time, you need to take that into account. Cloud computing is quite accessible these days. You can, everybody can get a cloud server. It's not cheap, so it's about $20 for a decent cloud computing service. And if you want to make this, to offer this to researchers, they will get what you have. So they can customize it only if they ask you, or you can have some sort of parameterization, but obviously what you think is important. So this is great for doing products rather than algorithms. So if you want to make some sort of planning algorithm that you want people to use for everything, that's not going to work out. But for example, if you want to make sketch generation, which I'm going to talk about, or if, for example, you want to get Mike's curiosity map, so I basically just give you a map and you give me back a play trace of the curiosity agent. That's pretty useful. So let's actually talk about the what I did. So this is a web service that can generate map sketches, which are game level, and I'll talk about that in a bit. It's a generic algorithm, so it tries to optimize towards specific objectives, which you can define. It can also evaluate either generated or hand-authored map sketches. You define which objectives it's evaluated on. It's a RESTful web service, it's coded in Java, and it basically consumes and produces JSON objects. The way it works is you have an application, or any researcher has an application. You ask through a post command if you want to generate or evaluate something. You provide the data structure through a JSON object. And the web service does all the computation and spits out a JSON response. And we'll see some examples of JSON responses soon. So map sketch is something that I started with a few years ago. It's an abstraction of a game level, which is very low resolution and provides only the minimal details that make this specific level a level for the specific genre. So it has different types of tiles. It's only grid-based for now. And you can have passable tiles, you can have impassable tiles, and you can have special tiles which are specific to a genre. So resources and bases for a strategy game that we see here, if I can learn to point. and weapons and health packs for a first-person shooter. Now, these low-resolution map sketches can be converted through different algorithms into more elaborate levels. So this can be converted into a strategy level, an endless legend level, and a first-person shooter 2-floor level, and I'm going to be showing those in my poster on Tuesday if you're interested in that particular thing. Now, if we want the web service to create a sketch, you need to define what you want in it. So you have a tile types array of JSON objects. You have the name of the tile type, the character that represents it in an ASCII map, because we're mostly working with ASCII maps. Whether it's passable or not, so for the Pathfinder, and whether it's the default tile. The default tile is optional. You can only have one true default tile, and that means where you're starting from. So in this example, you have name, land, ASCII character is dot, passable is true, name, water, ASCII character tilt, passable false, and it's the default tile. So that means that most of your map will start from C, and then it will start adding land tiles, etc. as it goes along. Great. I have to be online because I'm going to do a demo of the web server, so excuse me for this. So in order to evaluate the map sketch and evolve towards improving certain things, you need both a constraints array on what constitutes a playable level and a fitness array. So these are JSON objects. You can have multiple constraints, multiple fitnesses. Every one of these needs to have a name, a type, which defines what algorithm, what metric is going to run to compute the value, the score. It can have a weight, which is optional, and that allows you to specify how much you're interested in improving this particular fitness. And it can be -1, for example, where you're trying to minimize the fitness. And it has reference style, which is mandatory, and then depending on what type you're using, it can have target tiles and arguments. So the types of constraints that I had in the paper, and there's a few more that are work in progress, is the connectivity constraint. For example, you have constraints name, connect all, type, connectivity constraint, reference style, city, horses, and iron for civilization. So that says that any city tile, any horse tile, and any iron tile must be connected to each other. You have the numerical constraint, which is you have to have specific number of tile types of this type in the level. So, for example, city number, type numerical constraint, reference style city, and arguments equals comma 2. That means you want to have exactly 2 cities in all your maps. Conditional connectivity constraint that works like a connectivity constraint, but you can change some sort of pathfinding. So, for example, I could have passable C, even though originally my tile types I said it was impassable. If I want to check if I enable ship traversal, for example, civilization. And finally, there's a distance constraint, which says how far away different tiles need to be from each other. So, for example, city distance constraint, reference style city, and arguments minimum of 7. So that means every city tile must be at least 7 tiles away from every other city tile. So there are several different types of fitnesses. These are from work from 2013. Safe area threshold fitness, safe area threshold balance, tile safety fitness, tile safety balance, and exploration fitness, exploration balance. And in this example map sketch, we have reference tiles being the 2 triangles, and we have, if you have the target tiles being these stars, then safety, then you calculate safety by seeing how far away each of the stars is from the different triangles. So this one is not safe because it's equally far away from both triangles. This one is not safe because it's equally close to both triangles. And this one is much closer to the blue triangle than to the red triangle. So it is safe for the blue triangle. We could treat everything as an interesting tile, and we can set up a threshold. So this is the map for safe area threshold fitness with a threshold of 0.35. And we see that these tiles are safe for the red triangle, and these tiles are safe for the blue triangle. And we also have exploration fitness, which is how much effort you need to spend to find one triangle from the other. And that is done through Flatfill algorithm, which stops once you reach the other triangle. So this is going from the red triangle to the blue triangle, and this is going from the blue triangle to the red triangle. So as an example for the data structure, you have a city exploration of type exploration fitness, reference tile city. So you want to improve the exploration of the city tiles. So you want to place them far away from each other. And this is a more complicated one. I'm probably not going to go through it. Resource safe area, type safe area threshold fitness, reference tile city. Your target tiles are horses and iron, and the arguments are 0. So that means we want to find, we want to improve the number of horses and iron that are safe for any of the 2 target tiles, for any of the cities. And the any value of safety, anything above 0, because that's your threshold in this case. And there's more documentation obviously online. Right, when you're evolving map sketches, you need to specify some parameters for your evolutionary algorithm. The mandatory ones are number of runs, which defines how many results you get back, the size of the map, map size y, and population maximum generations. And those 2 affect how long it will take to spit out a response. Obviously, with low population and the maximum generation, you get instant feedback, it might not be very good. There's a lot of optional ones that are detailed in the paper that can affect how the algorithm performs. This is an example. Parameters runs 1, we just want 1 result. Maximum generation 100. Do we want to use fi to pop low? Population 20 and mutate toggle wall, which allows you to do custom mutations in your algorithm, a 5% chance. You can also give the algorithm, the web service, a template map. So I call this reference tile maps for no particular reason. It's an array of sketches, and it can be used to seed evolution. That means you can start from a specific point in space and evolve further. Or it's necessary when you're evaluating something, because you need to tell it what to evaluate. So case in point, when you're evaluating map sketches, you can use it using the sketch evaluator post command or the sketch detail evaluator post command. They both spit out scores, which are either the fitnesses or the constraints. They also you require reference tile maps, as I mentioned, and they tell you if it's feasible or not. And if it's not feasible, then it tells you how you score in the constraints. So how far away you are from being feasible. And if it is feasible, then it gives you the fitnesses. So in this case, resource safe area of 1, city exploration of 0, and 99, resource safe area of hours of 0. And it also gives you the asking method you provided to, in case you have forgotten, you need to keep track of what is being evaluated. When you use the sketch detail evaluator, it will provide you with several debug maps that that are used by the system to calculate things. So this is a distance matrix from city 1 in the entire map, and this is a distance matrix from city 2 to the entire map. And you have choke points, for example, or all the impassable tiles clumped together. This is the safety matrix for city 1, and this is the exploration matrix from city 1 to city 2. So all of these and more are coming out. You need to pick which ones you need. One of the things, like I'm currently doing whatever my generator already has. If you want to have it, you'll have it eventually. If you want to evolve something, you call the sketch generator post command. It must contain a parameters array, and it can contain reference map, tile maps in order to see the relation. And it will return n maps, where n is the number of runs. So this is an example response, which is basically this map and this map. So, 2 maps. If you give it, let's say, 10 runs, it might return 9 or 8 or none, because it will not return maps that are infeasible. So it will only return feasible maps. So this is the upper bound. If it returns no maps, then it's quite possible that you have poorly designed constraints. The problem is too hard. You might need to increase the maximum number of generations, things like that. And just to give a demo, I know demos really always work. So at semisketchbook.com, you go to web service. There's an error message. Bunch of stuff here. There's a documentation where I actually talk a bit more tables and everything. And let's start with an example. So these are basically things that I have already I'm gonna put 5 generations and a population of 10. Generate JSON. You see, this is the JSON for the roguelike. Several different things, obviously, including constraints and fitnesses. You get a result, which is this one. These are the entrances and exits. You have to go from here to here, or the other way around. Monsters are red, rewards are yellow. And you can also press evaluate JSON, which gives you, this is the command that you're sending, and there's the response that you get. So this has a pretty low treasure safety balance because I put it to ridiculously low number of generations, but it has a high duration balance, etc. And if you do the detailed version, it will give you all this stuff, very interesting for humans, but with a simple HTML thing, you can convert it into something slightly more readable, and you can use for a debug tool if you want to use it. For example, I use it for Summerville sketch to provide feedback to the player, or to do computations yourself. So you have a distance matrix, and you can just do whatever cool thing you want to do, and not rely on my safety matrix metrics. Let's go back briefly. There's also the free type version, if you want to dig deeper. So it creates a editable text, so you can just play around with these values directly. Not going to do that, but then you clickable from here, and it starts processing. Depending on how big the map is and how many generations you ask, it might take a little bit of time. So just to take something away from this talk is, of course, you're free to use this. Welcome to talk about it if you want some additions or whatever. What's important, though, is we need to find a way of sharing our work. If you can put it on GitHub, that's great. If that doesn't work, you can do a tutorial about it. We had some great stuff yesterday. We're going to continue promoting, giving tutorials. If that's not possible, or if you prefer, you can organize an AI research jam, a prog jam. If you're me and you can't do any of these, please put it on a web service, put it on the cloud, provide an interface for it, make it a bit customizable, and then write a paper. So that's pretty much it. Final. Yes. Thank you very much. Yes.
Just a short question. Currently, you just have JSON output.
Yes.
Would you be willing to do like CSV? I can convert it myself, but other structured formats.
Yes. I mean, it's just it's you could convert it yourself, but it's
Right.
not.
It might be easier though for you to write something.
Sure. It's just that it has several, it has a few data structures, so then it's just going to be
Okay.
because if you see the results here, and I'm not saying I mean, if you just want to create this, it's just a matter of removing some.
Oh, that's right. Okay.
So this is just output from the generator.
So that's one option.
So yeah, this is the JSON output.
Oh, okay.
Basically, it's just an array of strings.
Right.
If you want to do the evaluation, because it doesn't give you any evaluations, it's going to tell you, here's some maps. Okay? Then you need to run the evaluator on those maps. And then it will give you these. And these are kind of harder to I could, but it's not going to be easily read.
On a slightly same note, it might be nice, I don't know if it already does, if you could just, when you click it and it generates it, spit out a zip file with everything in it, as opposed to, a person copying and pasting.
Sure, yeah. I didn't,
the web page might be...
I didn't reach that far.
Yeah, but it might be kind of nice.
It's a good suggestion. But then the zip file would be just just a text file.
Yeah, or it could just be spitting out, I guess, but instead of just copying and pasting or something.
Yeah, no, I agree. I mean, this is, so, to be fair, this was supposed to be used, if you have a thing, then you just need the output, and then you don't need to save it as a text or anything.
Yeah.
You just directly take it and convert it into something that you can use in your tool. So, yes, I'm just since that was the goal, I didn't really get it.
When So if people set generations to 10,000, or in general, if they ask your server to do a lot of work, do the requests go into a queue? Do they get processed in parallel? Do they get canceled?
They don't get cancelled. It might take a while. I mean, it does respond asynchronously. So it will just come back after a while and tell you like, hey, I just finished evaluating the thing. I haven't tested it with like completely ridiculous values, so I can't really. I don't have the specs of what will happen in the web service.
Like related, have you thought about any security concerns?
No. What's that?
Yeah, agreed. And this seems like the the level generation DDoS protocol, right?
Yeah. Fair enough.
So it's it seems like the biggest. Tell me if I've misunderstood. It seems like the biggest contribution is the fitness stuff that you're doing, right? Because at least that's how I would look at it. Because otherwise, I'm giving you all this information, and you're just running a GA. I could.
Well, I'm running a constraint optimizer, which is not. I mean,
okay,
yes, it's not really. Yes,
yeah.
It's not rocket science.
So so maybe that's another thing. Your fitness stuff is rather unique, and then maybe you're going to say it's a lot faster than if I wrote. Well, minus the web lag and all that kind of stuff. It's a lot faster than if I wrote the genetic. And if I have all that stuff ready, why can't I just throw it into a genetic algorithm locally and do the same thing?
I mean, you can. It's just that I have made the map sketches so that they are kind of generic, so you can use them for many different games. With the caveat that then they're a bit too generic, so you can't really do cool stuff like what you were showing. Is this puzzle? Yeah, they provide a nice, easy interface for people that don't want to bother with coding a GA. I mean, I'm not sure I'm selling it to you, or no.
It's cool. I like it. Here's another question: can I, or have you thought about me being able to, in a JSON object, also give you a different fitness function? That's
would be great.
That's not trivial, right?
No, it would be great. Then I'd have to write an interpreter.
No, you've got JavaScript already.
Yeah. Cue previous questions on security.
Yep.
Yes. Right. No, I haven't. I don't know how to answer. It sounds like a really cool idea.
Yeah.
I'm probably not good at it. It sounds hard. Yeah. Yes.
I'm just sort of curious what lessons learned you had just from creating the interface. In some sense, it's like, have a bunch of operations, toss it into a RESTful interface. It seems straightforward, and I'm guessing that there were some decisions that had to be made, or some lessons learned in good ways and not so good ways.
I mean, so I've been working on Cerny Sketchbook for a while, and I went through a very a long phase where I was restructuring the code because at some point it was too organic, which means it was infested with music. So I did do that part, and I had a very easy way of, basically with an XML file, be able to make generalizable levels. So it was just a matter of putting that code into the web service. I didn't really do anything. I did take some design decisions, but mostly it was like, what can I fit in this paper, and the rest I'm going to have to work on to make better and more intuitive. Basically, if I make this available, people will come back to me and ask me for specific features. So hopefully I can have so.
whatever your.
Oh my god, it's dialed.
Sure, yeah. Well, I mean, it's community generated content. Watch out, Mario Maker.
Oh, okay. We got you go.
Right, we do a really crappy game and put that up somewhere and just propose that at FD. Monte can solve. We have hands with fingers on that can manipulate.
Well, dude, at the rate I'm going. Well, you haven't lost any fingers yet.
Yeah.
I've had close calls.
Testing.
But either way, we can dictate. My phone supports dictation now, so I will have Siri right there.
Oh man, I would actually love an entire paper which is on the dictation with Siri, but you have to have Siri as a co-author.
Yes, I would.
But, you know,
I will dictate the paper.
Action cartoon.
Yes.
Testing. Hey, there we go. Your ears are gonna hurt. Just a sec.
And the first time that Toad had a voice.
Although I will say, I think like.
I also hope you're getting this awesome Mario lore discussion while I test the microphone.
Well, I mean, Netflix is making.
That was like Link's catchphrase.
Netflix is making the Zelda TV shows.
The hottest games chat. Okay. Mic's working. I'm gonna switch us back into schedule just for a second. We'll be back in a sec. Bye.
Test 1, 2. Test.
Oh, it's 11:03. 11:03. Well, I guess we must start then.
Sorry.
Way to organize, God.
I'm not organized. I feel like I need to start having scripts for people so I can be like, this is Adam Summerville. He comes from. He was born.
Was born a white boy in Columbus, Indiana, which we like to go by Athens on the Prairie as I think in the advertising literature for it. Yeah. It's home to Cummins Engine Company, so if you have a diesel, if you're into diesel engines, anyway. But for things that are actually important.
Well, yeah, so
sorry, Columbus.
We're starting up again. This whole session is basically PCG themed. Really, you know, it's the Adam Summerville Power Hour, but whatever.
Woo.
And we'll let him take over.
Okay, so welcome. I hope you're okay with the sound of my voice. You're going to be hearing it for the next hour. So first off, sampling Hyrule, multi-technique probabilistic level generation for action role-playing games. So why action role-playing games? And by action role-playing games, I mean Zelda-likes. I don't know why action role-playing game is the term that's used, but it is. So they're a very interesting domain. I'd say more interesting than linear games such as Mario, which please ignore that bullet point during my next talk, where I talk about how great it is to do stuff for Mario. And this comes from the fact that they have a mix of like high-level concerns, like the plot points that a player must interact with, such as getting a key to unlock the door, to get the item, to defeat the boss. And then there's the low-level concerns, which is the actual level geometry that the player is moving throughout, which brings to the sort of middle level, which is that there's this non-linear progression through the level. There's lots of backtracking. You have to go to places. Maybe you see something that you can't actually get to yet, which, as opposed to in Mario, where you see what you want to get to because it's to the right and not to the left. And so to do this, I used Bayes nets. And so why Bayes nets? They are a generative machine learning model, not a discriminative learning model, which means that they learn the joint probability distribution, not the conditional probability distribution, which is sort of nice for something like this where we're not necessarily trying to learn a classifier of is this a Zelda level? We want to learn how all of the pieces of a Zelda level actually interact with each other. We're not trying to get to one specific thing. We're trying to get the sort of whole soup of them all together. And they're robust to missing data, which, for the sort of machine, the training part is maybe not as important because we have all of the data ahead of us. But at the time of generation, it means it's robust to missing designer input, meaning that a designer can choose to set whatever or observe whatever data that they want, and then the system can work around that. Or a designer can choose to set no data, and it can, again, sample from that space. So first, I'm going to give a brief little overview of Bayes nets, which I used for the generation of the topological, high-level topology of the level. And then for the sort of room generation, I used principal component analysis, and so then we'll get into that. And then finally, we'll smush those two together for the actual dungeon generation, and then I will conclude. So right, the data. The data came from fully screen-capped maps that exist from fandom on the internet. Thank you, internet nerds. You are wonderful. There are 38 levels from the 3 easily accessible Legend of Zelda 2D games, namely The Legend of Zelda, the first and second quests, Link's Awakening, and Link to the Past. There don't really exist any good ones for the Oracle of Ages, Oracle of Seasons, unfortunately. So internet nerds, you need to get on that. The dungeons consist of a little over 1,000 levels, and it was all hand annotated, which is really annoying, and I'd like to have an automated system for that. But there's some sort of tricky things that come out where rooms might not actually be rooms. In this picture over here, you might expect that sort of the green walls are what demarcates rooms, but there's actually things where there's this middle big room where there's this balcony where you can't actually get to the lower level from the upper level, and they're only sort of in the same space, and they're sort of connected by like that you can see the other from but there's no actual like door between them or no way like to actually traverse that space. So the concept of the room is not necessarily actually truly a room. It's just, the player could be in that space, and then the places that the player can traverse to or see from that space. So this is sort of what the annotation scheme looked like. Some of you might be able to guess what this is. If you've seen this talk before, you probably definitely can. So for each room, in this case, it's simple, where each room is its own room. There is, it was colored based off of what room type it is and has sort of other features to it. If I bring up this key, maybe it starts to become more clear that the salmonish colored ones contain enemies. If it has a purple ring around it, then it contains treasure. The blue node here is the start, that's the end, that's the boss. And then the edges between them note what type of door connects them. Plain is that there's no special door there. I think this is that it's locked, though that's bombable. Anyway, and so you can see this is actually the first dungeon from The Legend of Zelda, aka the Eagle. And so did this for all of the levels, and then from that extracted a number of different features from these sort of three, the low, high, and mid levels. At the highest level, we have sort of mission level parameters such as, does the level contain a boss key, which is true for the later Zelda games, but not for the earlier ones. The number of locked doors, number of bombs that a player would have to use to progress through the level. At the low level, we have just straight up like, how many rooms are there in the dungeon? How many of each type of room do you expect to see? And then there's sort of the per room level things, such as, does the room contain enemies, puzzles, what have you? And then there's actually, after running a simulated agent through it multiple times to sort of build up some statistics of length of optimal path or sort of a range of suboptimal paths, like what do the paths through the level look like? How many times does a player have to backtrack? Or if a given room, is it on the optimal path? Is it some sort of side offshoot that isn't actually on the optimal path, but a player might want to explore? And so this is sort of an example of a BaseNet. This is not any of the ones actually used. It's touch simpler, but very close to. And so there's these sort of per dungeon level parameters, such as the number of rooms, the length of the path through the level, etc. And then there's the per rooms one, which vary, so for each dungeon, there's these things are fixed, and then for each room, these lower parameters are fixed, such as how deep into the level is it along the path, and what type of room is it, and then what type of room did it come from. And the edges between these sort of are the conditional probabilities within this entire joint probability distribution. They're not necessarily causal. You can flip these arrows and wind up with roughly the same type of thing, but it sort of is helpful to think about it when you're constructing such a model, that we might expect that the length of a path through the level would have some dependence, that the depth in the level might have some dependency on that, such as it's very unlikely to find a room in a level that is past the maximum depth of the length of the path. And we might expect, again, like the type of a room to vary based off of the type of room that you came from. For the consideration of this, we considered a number of different models. First, a random model, which took all of the different features we had, randomly assigned edges between them, number of edges based off of the same number as in our full model, just to use as a baseline, make sure that there was some notion that what we were doing was a correct way of doing this. I said we weren't learning a classifier, but we sort of acted as if we were, and acted as if we were going to try to figure out, based off of all of the other information, how many rooms do we think there are in a level? If I see a room at depth 28 in a dungeon of boss type, like how many rooms do you think that there were in that level? is sort of what we were trying to figure or trying to determine. And so we did a naive-based classifier where all of the things were conditioned on the number of rooms in the level. And then we had the full, which has every single thing, all of the features set up in the way that sort of captured our best intuition for how this would be. And then finally, the sort of sparsest subset of features that could still sort of meaningfully generate things, which was about a fifth of the size of the other models. We had 34 levels used for training, held out 4 for test, and then for the test portion, we stripped out the number of rooms and used that as the check. And we used the Bayesian information criteria for model selection, which I'm sorry, I'm going to show a little equation. I don't have any red text popping up saying not to look at this. It's a notion of the likelihood of how well the model actually predicts the data, as well as a penalty for how complex it is, trying to avoid overfitting a model. And so here we see, and note that Bayesian information criteria is sort of strictly negative, so the closer to 0, the lower in absolute value, the better you are. And we see that the sparse model had the best results. The full and the sparse were an order of magnitude better than the others, and the random was just obviously terrible, which, hooray, we beat random. But interestingly, the sparse model was not only the best mix of predictive power and complexity, it actually just had flat out the best predictive power and was the best at determining both for the training data how many rooms there were and also for the test. So that's the model that we used going forward for the generation, since it seemed to do the best. Right, so that's sort of the high-level topological structure of a dungeon taken care of. But for a player to actually be able to play it, there need to be rooms that they go through. So to that, we turn to PCA, or Principal Component Analysis. Right, so this was inspired by the work of Noor Shaker and Mohammed Abujlaika, and also the Eigenfaces work. So what you do is you first take a room and split it into a binary bitmap for each tile type. So I think there were 9 different types of tiles that I considered, so empty, had a wall there, had an enemy, had a key, etc. And so you have an m by n room, and you squish it into a single 1 by m by m vector, and then you do that for every single room, and you wind up with a k by nm matrix size matrix. And then you perform principal component analysis, which finds the eigenvectors of the covariance matrix, and they're orthogonal and in descending order of how much of the covariance they explain away. There's sort of no real notion of like what number to choose, but we chose the top 20 because they sort of line in the sand of 95% of the covariance, and that's 20 was a nice number. The 2 nice round numbers sort of linked up. Hooray. Science is done again. And so these are the top 5 most important PCA vectors for the sort of whether a tile is solid or not. And you can sort of like, the lighter they are, the more weight there is there. So this one is there's like a giant solid block in the middle, although it's more likely that there's these sort of like horizontal walls, or there's maybe a center column in the room, or maybe 4 columns around the outside, or anyway, this sort of like right side structure, etc. And so we have these for each of them, which is sort of this condensed feature space, which we can now, for each room, we have the like weighting of these that, when multiplied by gets you back the original thing. And we can use these to sort of interpolate between. So we would have, an existing room here of type enemy, and another existing room of type enemy, and we want to be able to, sort of smoothly transition between them. And you can see that, as we sort of vary which weight, the interpolate between their weights, we can sort of wind up with levels that exist, or rooms that exist somewhere in between those two. In practice, in theory, any 2 level or any 2 rooms could be chosen. You could interpolate between them. You could also just randomly search through the space, just try different weightings and see what you get. But in practice, you wind up with sort of a fair amount of gibberish if you do that. So we first performed a clustering step to make sure that rooms with similar weights wound up in the same, or what were chosen to interpolate between, because you might wind up with one where it's like there's a solid wall in the middle and a solid horizontal wall, and then you try to interpolate between them, and suddenly you have an impassable room because there's no way to get through the vertical and horizontal walls. So winding up with things that sort of actually wind up being traversable. Right, so now we'll actually get into the actual putting these two together and the dungeon generation. Right, so we have the BaseNet. And so for the purpose of what it was done, we could imagine observing any data. I only observed the number of rooms, set a number of rooms, let the system determine what the sort of other conditional probabilities should look like, and then from that, sample from these probability distributions to get what they should be. Although some of them are determined, like for the first room we're generating, the depth is by definition 1. And the room you came from is the sort of non-existent null room. And then infer the rest of the data that we care about, which in this case was only room type and the number of neighbors. And then for each, so we would observe a room, and then for each of those neighbors, we would then set its depth to be something new, and what room it came from to be the previous room. And we keep doing that until we've wound up with a number of rooms that we want. Note, this does not necessarily give you anything playable. In fact, it's very unlikely to give you anything playable. So there's a couple sort of post-processing steps to make that actually come together. Right, so we can imagine many different conflicts. So say, for instance, that this door is locked, but you might notice the key is up here. What are we going to do? The sort of nice thing about the way we did this is that we have the likelihood for every single room. And so what we can say is, well, okay, which of those is probably most likely to contain a key? We can go back to each room sort of in front of this locked door and say, well, what are the odds that you contain a key? So something like the start, you very rarely walk into a dungeon and find the key. That's, very unlikely to happen. But maybe in the room a couple deep with an enemy in it, maybe that's a pretty likely place to find the key. So we can sort of move it there. And we can also imagine, changing this in a different way, and also saying, well, okay, which door do we think past the key is most likely to be locked? And therefore, we can move the locked door to be behind the key frontier, and we keep doing this until all of these conflicts are resolved. Additionally, things that we want there to be some sort of constraint on, such as there's the same number of keys and locked doors. We can just flip a coin, decide, should I erase a key, should I erase a locked door, and then using the same sort of likelihood information, determine what the best place to do that would be. Similarly, we want there to be a start, we want there to be a boss, we want there to be a Triforce at the end, sort of making sure that those all exist and setting them up in that way. Right, so we did this for a large number, for different sets of rooms, or different sets of levels, those with the smallest number of rooms, which were 12 rooms, sort of the closest to median value of 35 rooms, and then a larger level of 47 rooms. And we generated 20 levels, and then wanted to compare their likelihood back to the existing levels that exist. And we're not there. The blue is the human levels. They are universally more likely than the generated levels. The spread gets worse as we keep going. On average, the sort of penalty is that the odds of making a level is sort of on average about the penalty of adding an additional room or so. So we're off by a couple of rooms perhaps in terms of likelihood. So I'm not exactly sure if this is the correct measure. Just because something is less likely does not necessarily make it not as good. We could choose the most likely thing at each time, and not do sampling, but you sort of get railroaded then and maybe is not perhaps as interesting. So I think it's still an open question as to what the proper way to evaluate a system like this is. And yeah, anyway. So here are examples of some levels. This is started to give you the high level overview of what the general topology kind of looks like. And then to get a look at what the PCA does, we'll do zoom and enhance. And I think that this is a puzzle room that should generate a key when you probably push one of those blocks is sort of the intention, I think, that the system had. Rooms with enemies, and it looks Zelda-like. Right. In conclusion, I first learned a Bayes net for the topological features in Zelda levels and used principal component analysis inspired by eigenfaces to construct a sort of reduced feature set to then interpolate between rooms, sampled from the Bayes net to construct a level topology, resolve conflicts, constructed rooms, and then used the BIC as a novel method for level evaluation by comparing the likelihood. And with that, I will take any questions.
Did you give any consideration or think about either trying to measure or replicate symmetry? That's one of the things in multi-line.
Yeah, you mean like at the room level, because like these are amorphous blobs and not looking like the eagle or something like that.
No, I mean
or
within a room, interpolating like in a symmetric way as you're turning on things, because a lot of times you're interpolating from room with symmetry to room with symmetry, and there's no symmetry in between. You know, so it doesn't feel handcrafted.
Yeah, no, there was no measure. I mean, if you remember, the PCA blocks tend to actually have a fair amount of symmetry, and you're right, there could wind up with ones that, you know, where there's not symmetry, but yeah, no special. I mean, you can see that it does wind up with some like symmetrical things like that, or say that guy or that one. So it does occasionally generate these symmetries, but there was no consideration in the interpolation process to that.
So you mentioned the sort of how to make the levels playable
Yep.
section. How does the system actually recognize the conflicts?
How does the system recognize the so I run an agent through it, and if it can get to the end, yay, it's playable. If it can't, then there's typically some like locked door that it can't get past, or some there's sort of other notions of locked door, like maybe you can't find the special item before you need to pass a puzzle to do that. And so I sort of look at whatever the furthest point in the frontier is of, I know which rooms it can reach, and so then I know also which rooms it can't, and so I know where it's locked, and yeah.
It's kind of interesting, I didn't have that question, but so it's kind of interesting that you run the agent, I assume, only on the general idea that this is a room with an enemy, and I don't care about its topology, right?
Yeah.
So the topology could also make it unplayable as well, right?
You mean like in the per room level?
Yeah, the per room.
There is, so I do also guarantee that if a room has, huh?
It's not with the agent.
Not with the agent, but I do just say, well, okay, if like these are the doors, you must be able to reach those doors from the thing. But yeah, there is also a keep flipping coins with when it's so after the topology is constructed and then it does the room level, it just keeps saying, oh, I'll pick two at random, try interpolating between them. Does that hold for the conditions I need, such that I enter from the lower door and exit through the upper door?
Have you thought about using your agent for analysis of the final result as another way to kind of get at like quality?
No. I mean, so I guess like, right, I mean, well, I guess yes, since I used it to determine if it was playable, which is obviously some measure of how good it is, right? So right, there's a sort of a binary good or not. I think I'm not sure what. So that's right. So that gets fed into the probability at the end of after I've constructed it, and I run an agent through and get all of the information about all these rooms, about the backtracking, etc. That then gets shoved into the probability distribution to tell us how likely it is. So in some way, yes, like it's used. It uses the what that produces in part for the scoring, but not solely. It might be interesting to look at just those measures as opposed to other measures that are perhaps like, did the number of enemy rooms, maybe that's not as necessarily as interesting measure. So maybe weighting or looking at only specific measures of likelihood.
Oh, sorry. Go ahead. Well, we're just exchanging questions. Can you go to your results slide?
I can.
So, I guess the underlying question is why did you use pick as your performance metric? But basically, my actual question is why are human design levels scoring much worse in larger maps?
Oh, in part it's because, well, so there's two reasons. One, I would not actually use the Bayesian information criteria again because there's this additional, we don't care, we have the model, we don't care about the complexity at that point. That should just get thrown away. Only the likelihood is what should matter. So, right, by definition, as we add more things, we're making it, like we can only get less likely, right? If it's adding another room that's of 1/20th probability and we add 20 more rooms, we're now 1/20th to the 20 less likely, just by the sort of the nature of how this is going to play out. Yeah, so that's why it gets less likely as you go on, just because there's more things that are there that are going to have some low probability to them.
Yeah, I'm trying to think how to improve that.
I think so. That's why also that we chose the points to generate it at, because essentially you can only compare within a given number of things to try to correct for that portion of it.
So, kind of a common critique of procedurally generated levels is that you cede a lot of authorial control to the algorithm, but then we always say, well, but at least as the developers of the algorithm, we're tweaking the knobs and we, therefore have authorial control through the algorithm. And so it seems to me in this work like you're then also ceding authorial control over the algorithm. And so then I guess my question is, isn't this worse in some sense, right? Like as a level design, as a level designing programmer, you now have effectively no control over what comes out because it's all coming from the machine learning algorithm, and then that's generating the levels, based on the probabilities of things you've observed. And so aren't we worse off in some sense? So, comment.
So no, yes, I think I take umbrage with that belief, but right, I'm going to sort of paraphrase Adam poorly in something like this, that right, for all of these generators, there's some sort of latent semantics that are typically are implicitly defined and pretty much implicitly defined poorly, I would say, unless you're using something where you make very specific commitments to the semantics of the generator that you're going to create. So I'd say that at least here we're seeding it in a way that we say that these are things that we like, and we want to create a system that could generate things that look like what we like without actually making specific commitments to how we should go about creating those. So I would say that it actually opens up doors of being able to, and maybe this is a first step, perhaps not the final solution, but I would say that it sort of helps us go towards a way of saying, I know the levels that I like, I can show you the levels that I like, I could draw you a level that I liked, but I might not be able to perfectly elucidate every single step that goes into that. I don't think we've created rules for art and music and et cetera, and so it's, I think, a different approach, and I think opens up new possibilities. So, but still, while allowing for, a designer can sort of, at this level, you could either prune the corpus to be the things that you like, or also there are knobs that you can tweak to sort of help guide it into a way that you want when you're generating. So
I'm actually, this is really fascinating to me as an approach towards designing some of these designs and understanding some of the commitments we're making, et cetera. I was actually curious, is you kind of opened by saying we're going to generate Zelda likes.
Yeah.
And then we generate Zelda. And so I'm just curious, in terms of what you're doing, are you thinking about this problem, or how would you approach the problem of actually trying to start to generalize? So it's not, here's this very stereotypical broader class within which Zelda is a member.
Yeah, I definitely think that that's an interesting way to go. In all honesty, Zelda is probably not like the best place, right? There are not a lot of Zelda-likes out there. Like it's a relatively small space compared to like say like platformers or something where we could have like we have this very rich space of platformers that we would perhaps want to get a whole understanding of all platformers, and it's much easier because there's a lot more of them and so more data points. Like like there's Zelda and then I don't know, Soul Blazer and Landstalker and like there's some, but it's like you're looking at like maybe 10, 20 games as opposed to like hundreds. So I definitely think that that's a good way to go, but maybe not with Zelda, or at least maybe not with Zelda yet. But yeah, definitely.
Do you have plans to make it playable by humans?
Sorry, what?
Do you have plans to make the results playable by humans?
I would like to. There is sort of an open source Zelda framework that exists. For the sake of getting it into a paper, it was easier to just throw up PNGs. I looked at it. The file format's not that intricate, so it's not probably like it's work, but it's not impossible work or anything by any stretch of the imagination. So.
Would you be interested in throwing that at like mechanical Turk to try to get human evaluation? Is that useful?
I do, although, and I think this is a whole separate subproblem of the fact that, like, right, human evaluation requires humans and humans who wants to deal with them. So I think that the open question of like how would you algorithmically or with a computer evaluate levels, and I think that an interesting thing is like I threw the original levels into this thing. Not a lot of people have been there have been measures of like linearity versus leniency and the expressive range of a generator, but how do actual original Mario levels, or how do levels that exist in this space actually look? We say that this is the expressive range, is that actually relatively close to the expressive range that one might expect from these human author or levels that we were sort of maybe trying to target or something? So I think that that's a whole another open question of how would you do this without humans. But yes, definitely humans too, because humans exist. And
we need to questions so that Adam can stop talking. So Adam can
start talking. Sure.
But thank you again. Let's.
Yeah. Yeah. Also, yes, we can.
But first, a man who needs no introduction.
Adam. So hello, welcome again to MCMCTS PCG for SMB, using Monte Carlo tree search to guide platformer level generation. Right, sort of platformer level generation is, I think, the most widely looked at version of procedural content generation for levels. There's sort of been a wide range of classical AI approaches, with either reactive planners or constraint solving or rule-based systems, and then sort of more recently moved towards sort of statistical AI approaches, such as Sam's work or Matt's or others, of using machine learning techniques to try to generate levels. And these two things, getting back to Jim's point, that the classical approaches sort of offer up more control, right? You are specifically designing the level generator or hopefully in a way that you understand fully what you were doing, but you're giving up some sort of ease of design. It's harder for a person to come in and start doing that. And the statistical approaches have sort of the converse problem where you have your corpus, you train your thing, and at that point, it's very easy to start, you can do that. It's not that difficult, really, but you're ceding a lot of control to the things that you're learning from. And so the hope is to sort of find some way to meet in the middle. And so for this, we proposed using Monte Carlo tree search as a way to guide machine learned creation that requires a relatively small amount of design knowledge while still offering up sort of authorial designer control. So first, I'll give a brief primer of Monte Carlo tree search. Perhaps preaching to the choir here, maybe you all know Monte Carlo tree search, but anyway, still you'll get a little primer on it. And then what I'm calling Markov chain Monte Carlo tree search, not to be confused with Markov chain Monte Carlo sampling. So horrible, everybody wants Markov chains and Monte Carlo together, and anyway. And then finally, we use this system for a player modeling study, and then finally, which we hope to use later to inform additional work on this, but is not yet in there, and then finally conclude. So right, Monte Carlo tree search, by which I actually mean Monte Carlo tree search with upper confidence bound 1 applied to trees, or MCTS. It's most commonly been used as sort of an adversarial game AI, represents sort of the state-of-the-art adversarial AI in games such as Go. And a nice thing about it is it only sort of requires a terminal evaluation function. We're not like creating heuristic. We don't need to worry about that. And it's, typically, we don't even need that evaluation function. We can ask the simulation, did I win, did I lose? Done. I don't need to worry about it, which is nice. And so there's also a sort of trade-off parameter that allows us to determine whether to exploit promising paths after we've seen them, keep going down that, I think that's a good way to go, or also explore new paths that you haven't seen to sort of get this sampling across the tree. And so for high branching factor games, it can get much deeper into a tree. And it's also any time. So at any point, we can stop, get the best result, and go ahead with that, which is very nice if time constraints are an issue. Right, so MCTS is composed of sort of 4 sections. So here we would see sort of an example mid-process. We're going to select a move. We started at this topmost node, and we want to select which move that we should take. And we'll say that sort of darker is better and lighter is worse. So for the selection phase, at each decision point, we look down and say, well, which one do I think is the best? Okay, which one do I think is the best? Oh, okay, I get here. And this has not been fully explored. And so we will now expand. And we expand it out. These are unexplored. And we take the moves at that point and choose one of them at random. Say this one. And then we do what's known as a rollout, which is we essentially keep flipping coins and say, OK, at this point, I'm not going to do anything smart. Just start making random moves. Everybody takes random moves. This is the Monte Carlo sampling portion of it, where we just say, OK, just going to sample it a bunch, get to the end, get a score, and then use that. And so there we get a score. So it was light. Maybe we didn't do so well. And now we backpropagate back up with that score feeding back in. Normally there's some sort of flipping back and forth, but here this is all one player. Since for the purposes of level generation, it's only one player. And so yay, MCTS if you didn't already, or anyway. So now using MCTS to guide this sort of Markov chain generation. And now, first, a primer on Markov chains. So Markov chains, you have a state, and then you have transition probabilities to new states. And sort of typically, they are historyless. So once you get to a state, it doesn't matter necessarily how you got to that state, just what are the things that you can transition to and the probabilities you transition to them. This is not actually fully true. There's often Markov chains with additional history, but that's sort of actually just composing composite states out of other states and just weighting the probabilities accordingly. And so we can keep doing this and expand out in the tree, and there's different probabilities of getting to different places, and we can keep doing this forever. So right, Markov chains have been used in a lot of work. Steve Dalskog, Sam Snodgrass, and right, they represent a very sort of convenient, intuitive method for constructing levels from existing levels. We can imagine, particularly for Mario, progressing in order and choosing what the next thing to place is. And so for a given tile, or in the case of what I do, and Dalskog did, a sort of column of tiles, figure out what, based on the different states that we can transition to. How many times have you seen that in the training corpus versus how many total things could you see? Choose it with that probability, and you can keep doing this until the level is constructed. But so a drawback of that is that like the playability guarantees are very low. I think stealing from Snam's work, it's maybe roughly 50%, or at like some of the worst ones, it's maybe 20%. So you're sort of flipping a coin every time. But there's sort of this nice analogy that we're flipping coins and randomly selecting things, and that's exactly what a rollout is in Monte Carlo tree search. And so we can sort of directly lift that and put it into the Monte Carlo tree search, and we're sort of just doing this a lot of times and flipping these coins. So here's what our sort of data level looks like. We have, nice Mario 1-1, and we look at the left twomost columns, and then the different things that can transition to. And so there are some sort of sacrifices made for the sake of speed and expediency, where we don't actually necessarily consider just the next thing or the next two things, etc. We actually consider up to the next 8 tiles. Admittedly, these are sort of weighted less probabilistically, so it's unlikely that you'll sort of string together a lot of these, but it's a possibility. And this is sort of a sacrifice made to speed up the rollout, so we can generate a lot of levels very quickly and build up better statistics. So the concessions made, consider 2 tiles as the history, and then larger chunks. Right, so we'll sort of walk through a little example. So say we start with these 2 as our level, and so that's our current state. And say this is what we choose as our next piece. So it gets slotted in the level. We have a new current state. Say we select that. We keep doing this. And we string together a bunch of stuff. And now we're at this state, and we can choose what to do next. Right. So the Markov chain Monte Carlo tree search, as I said, the Markov chain construction is equivalent to a rollout. And so right now we're at the stage of, well, what's the designer control? What's the evaluation function? And right, it's hard to evaluate levels, as previously discussed. So right, there's some simple level evaluations that we can do, like is the level playable? And then also like what are the proportions of tile types? Like are there more enemies, more coins? These are sort of simple things that we can choose to balance for. So right, solvability is determined by a sort of tile level A star, not as fancy as like Robin Baumgarten's, but much faster. So instead of taking 30 seconds to run through a single level, we can run through 30 levels in a second or so, and much faster actually. But anyway, so we can generate, again, we're just trying to flip more and more coins. And so the observed probabilities are not actually necessary because we're sort of smoothing over that with the MCTS, but it does sort of help guide the rollouts into likely areas and also help us sort of maybe produce more Mario-looking levels. So really there's only one decision point, which is the evaluation function. And so for this, this is sort of arbitrary, but you could choose any number of things. We have, is the level solvable? It's a very low number if it isn't. In this case, negative 50,000, which when pushed through a hyperbolic tangent comes out to essentially, well, actually, I forget, it was -1, 0, whichever one. Doesn't matter. we're doing a sigmoid function, so we're sort of at like a -1 to 1 range, or 0, 1. I'm sorry, my math is fuzzy right this morning. Sort of based off of the intuition that most Monte Carlo tree search algorithms are looking at sort of a binary, did I win, did I lose? But we sort of want some gradient in between that, even in a level that is not solvable, we'd still like there to be more of the types of things that we want to see. And so we have 3 different parameters of the difference between the desired number of gaps to jump over in the level versus the actual number of enemies, and number of rewards, which is coins and question mark blocks and power-ups and what have you. And so we used this to score it. We had 20 levels from Super Mario Brothers. They were limited to 30 seconds for generation, which worked out to approximately 200 rollouts per each move. Each time it was selecting a new tile to place, 200 rollouts.
Can you go back one slide to the evaluation function? Are there missing absolute values around these differences here?
Yes. It's actually functions based off of those where, but yeah, typically just sort of square error, but. Yeah, no, essentially, yeah, square these absolute values. Again, slightly arbitrary, but yes. So here are some sample levels that it generated. The top, it was told to produce a relatively simple level, low number of enemies, low number of rewards, low number of gaps. Hence, you can see there's 0 gaps. There are some sort of choices that it makes that are sort of not necessarily the choice that, like, say, existing Mario levels use, where a simple level like this typically does not contain like a bullet bill shooter, but because it just thinks of that as an enemy, it will place those as readily as it would a Goomba. Here we see a sort of nice underground stretch that it does, although it's perhaps maybe directly too cribbed from level 1-2 from Super Mario Brothers, sort of directly copying it for this portion over here. And then also sort of interesting, maybe it's we can attribute a motif to the generator where it sort of does a thing here and then does the same thing here, but then sort of switches it up. So maybe this is a nice sort of representation of like, oh, well, I'm going to use things before. But no, there's no knowledge of that. But, you know, it's sort of an interesting, you know, artifact of it. And then finally, a sort of high gap, high enemy, which has sort of very recognizably Super Mario Brothers type design patterns, like the pyramids and what have you, but sort of in a configuration that you might never actually see in an existing Mario level. Typically, they're not quite this enemy dense, and you're not finding pyramids constantly through a level, but sort of interesting choices that it made. Right, so it's not guaranteed to produce a playable level, but essentially failure can occur when all 200 rollouts fail. If they produce unplayable things, and sort of going off the back of the envelope, 50% failure for a single level generation, then the odds of failure are about 1 to 1.6060. There's only 1 E24 protons in the universe. So, you know, it's possible, but it's, you know, sort of, we'll say unlikely that you have all of them failing. So, yeah, so it's, you know, sort of pushing it much better to that these are actually producing playable levels. Right, so we use this system for a player modeling study with the hopes of feeding that back into our scoring function to help guide future generation. We had 16 students. They each played 8 games. We had 8 variants. You know, we have 3 variables, binary variables, 2 to the third. They played in pairs, and then were asked which one did they like more, and also which one was more difficult, and then also what their experience level was. Are they a beginner, intermediate, advanced player? So first, we just wanted to check and see, is there some strong preference to the ordering that they play? If that is there, then that's bad. There isn't. There's no strong preference. It's not statistically significant. Also, the challenge rating is also not statistically significantly different between playing a level variant first or second. So we can sort of move ahead not worrying about that. Admittedly, we only have 16 students, so our statistics are perhaps not the best, but in, you know, pushing it up to a larger scale study would be better, but anyway. Right, so for player modeling, we used the variables put forth by Peterson, Tegelius, and Yannakakis, sort of divided up into like 5 categories of time-based ones, how long did they spend as Big Mario, etc. Jump-based ones, how many jumps did they perform, death, how many times they died, and what ways did they die, enemies that they killed, and then also other things such as like, how many times did they press the run button, how many times did they move backwards, etc. And then for feature selection, we used the AIIDE information criteria, and then used logistic regression to determine, given a sort of pair, which one do we think a player would prefer, or which one do they think was more difficult. And since we had admittedly very small data set, we used tenfold cross-validation to sort of avoid overfitting. Right, and so for challenge, so these will be presented as the odds ratio, which is if you see one of these things, in which direction does it push you to be more likely, like, yes, it was more challenging, no, it was less challenging. And so we see that adding more gaps pushes it more challenging. This is, the intuition that we had going in, so it's nice that our intuition is borne out, but that's what the algorithm shows. Our model was around 72% accurate with a kappa statistic of 0.45, which puts it in the fair to good range. It's not great, but it is fair to good. And then as you're more experienced, gaps phase you less, so they're less likely to find it challenging, but everybody universally sort of finds that enemies are difficult. For preference, which admittedly is sort of a more tenuous thing, more player-specific than necessarily challenge, we didn't do quite as well, 64% accuracy. Sort of interestingly enough, as you were either as you were more experienced, you liked rewards less, or as you were less experienced, you liked rewards more, which is perhaps is not interesting, but apparently rewards not important to more skilled players, and also enemies less likely to, sort of actually confusingly, as you're more experienced, you are less likely to like a level as you had more enemies, even though you didn't necessarily find it more challenging, just didn't actually prefer that. Right, so those two previous ones that we would hope to use in scoring relied on this notion that we had sort of perfect knowledge of a player's experience level. But we don't necessarily have. Typically, games don't ask players to fill out a survey prior to playing the game. And so we'd be able to want to guess, determine that based off of seeing their performance in the game. And so we see that sort of unsurprisingly, if you get, as you do sort of more difficult things, such as killing enemies with a shell, or which a beginning player might not even realize that they can pick up a shell, or probably would kill themselves in trying to kill enemies with a shell, or jumping on bullet bills, which are, sort of moving in a different way than, say, a Goomba or something. Those are good indicators that you're a more experienced player. And then, sort of, if you die a lot, you're less likely to be a good player, which, not necessarily surprising, but also good to get. Right. So in conclusion, Markov chains represent this sort of nice intuitive representation for learning from existing levels. And Monte Carlo tree search is an attractive option for search in a space where the heuristic is impossible or difficult to come up with. And we have this nice sort of synonym that the Markov chain generation is equivalent to a Monte Carlo tree search rollout. And then we performed a user study to help guide future work. We had about 70%, but 70% times 70% puts us at a coin toss. So obviously, we'd like to be able to do better to be able to guide future generation. And with that, I will take any questions.
What was the typical branching factor for the MCMCTS?
I don't know. I'm gonna.
I guess this would be.
I can compute it from the data I have. I'm gonna say 8 or so typically, but that's my rough intuition. But I'm.
That was the approximate number of outgoing edges at any time?
Yes. Does anyone want to go back to Zelda, since apparently this is not...
So 8 is pretty high for branching factor, obviously. But like, there's clearly certain areas where the branching.
There's also ones where it's like 1 or maybe 2 or something.
Sure,
yeah.
Sure. So is it
particularly the underground levels are very much that there's just not as many.
Yeah, there's less of them. So then, is it possible maybe that you could have used something besides Monte Carlo tree search that you might have actually been able to more fully explore the space of possible levels, especially given this low branching factor?
I mean, certainly you could, do a.
So is there a notion that like that fully exploring the space would just taken like crazy amount of time, or is that sort of reasonable thing to do?
Well, so let's see. We get about, so there's 200 rollouts per generation. So, and we go too deep. So even just sort of randomly exploring the tree, say on average about 50 times 200. So maybe about 100,000 levels is the depth, is what it's looking at. So I have no notion of, right, with a branching, like, I mean, 100,000 is, I'd say, probably not anywhere close to what you'd need to get to sort of fully exhaust or even come pretty close. So I think that the MCTS is buying you something there, but I haven't run any experiment to that effect, so I don't know.
So it seems like that because you're using Monte Carlo research as an optimization for a metric that doesn't actually include the probability of the level under the Markov chain, that the actual weights in the Markov chain are not important in the end, other than the fact that they were non-zero in certain cases. So that gave you sort of like a rigid language bias that said, like, after this, only 8 things can come after it. Not all possible things, but the relative weight of them was, in the end, not used. Or not.
Yes, the weights that are learned are certainly not the weights that are represented at the end, I think is definitely true. As I sort of mentioned, like, it does sort of help perhaps guide the rollout to slightly more likely spaces through that. So there is some, they exist in some way. Obviously, the sort of, whether it's 0 or exists is, you know, the sort of most important factor of that, but.
Why not include the wide likelihood as one of the features of that function that you're optimizing, so that it actually tries to use them?
I mean, yeah, that would be a certainly, again, I think this gets back to, is like likelihood actually a good measure? Like, right, just because we could choose the most likely thing at every step, but is that actually going to lead to, or, you know, for some measure, is that going to lead to an interesting space? Like, does that sort of more heavily constrain it? Like, again, I think that's open, and I don't know, but, and so maybe as just a feature of it would be an interesting thing, but I don't have any intuition as to whether, yeah, like how likely a level is actually a great measure for how good a level it is. But
You did a pair modeling user study for this, and
well, so we did. Another member who's not here did, but so I can't necessarily speak too greatly to the player modeling study and the design choices made. But go ahead. Sorry. No, not yet. So certainly not at the player modeling, and we also have not actually incorporated that feedback into like the model. So no, and in the future work also no. This is not one of those ones where it's like, and we did future work, and oh, by this point in time, we've actually done that future work. This is future work that is still yet future work. But yes. I don't know. It's a good question. Right. I mean, it's obviously there's obviously a player component to it. It's like the sort of challenge is the sort of where the player and the level meet and butt heads, and that's where challenge occurs. So there is the sort of the two halves of it, but like I do think it is also necessarily predicated on like, well, what does a specific player find challenging? And also there is also, you know, the open question, like, is sort of tailoring content to players like necessarily where we want to be? Like, Super Mario Brothers 1 is great, but it has no tailoring of content based on challenge level. Like, you know, these are, I think, again, I don't know. It's, I think, an open question to the field as to, like, we sort of always talk about, like, oh, we can generate anything for any player, but, like, is that actually what you want? Is that actually what a designer finds interesting? You know, and again, I don't have the answers to these questions.
Yeah, sorry, just to clarify, was when I was saying the challenge part wasn't the tailoring aspect of it, but sort of knowing that the level you generate was challenging or not.
Right. That's
that information into however you choose to generate it. So the Monte Carlo tree search, as far as I
outside of some parameters that you're giving it?
Certainly, yes.
And that was kind of the question I was trying to address.
Yeah, that's sort of what I was talking about, is like using these sort of player modeling of like, did you find this thing challenging or not? And like, therefore, can we say based off of like, if I see this level, do you find it challenging? Is that like, do we want to be like in the scoring function now, there'd be like a challenging knob that says like, well, do we want to be trying to target a challenging thing? Do we not want to be charging? Do we want an easy thing? You know, yeah. And I think like the hopes would be to use that, but again, as I said, like we're able to get with 70% accuracy a player's experience level, which is the sort of challenge score is predicated on that. So again, coin toss level, and so maybe our intuition is just sort of the way to go, but and we're still at coin toss level. So, you're fine. All right.
So I know that embedding markup chains is a pretty common practice. You'll have a high-level markup chain that will generate some distribution that you then run a lower-level markup chain over to generate some stuff. Do you think that embedding an MCTS search inside of an MCTS search might be a useful way to generate content?
An MCTS search inside of an MCTS search?
You run an MCTS search, generate some high-level distributions, and then you run a next-level MCTS search over those distributions to find like a thing to make.
Maybe, I don't know. I have not considered hierarchical MCTS before, so for level generation. So run with that, you know. That's yours, Jonathan. Okay. Anybody else? Good. Okay. Aw, cup.
Good time.
Just a glitch in the matrix.
Yeah.
So.
Oh,
yes, of course.
Attach it to Jeremy instead.
Yes. God, you mean like I don't get to just keep talking forever and just keep the microphone to me forever?
You can kind of commentate from the back.
Yeah.
Great slide by Jeremy there. Clip them on.
I'm never going to get tired of saying Mike has like I just won't. So this is Jeremy, and he can talk.
Yeah, I can talk, definitely. Yeah, I can talk for about half an hour. Right, or maybe longer, because I have far too many slides. Right, so this is the title of the paper as originally submitted. So we're going towards this idea of using conceptual blending to generate games. And this is joint work with Joe Cornelli. OK, so the context of this work is a EU FP7 project called CoInvent. Goldsmiths is part of this network of 7 universities who have come together with this really grand plan in a 3-year project of doing what it says up there, right? Building a computationally feasible, cognitively inspired formal model of concept invention. And importantly, that's kind of drawing on some very popular ideas from cognitive science, especially about how concepts are formed using a process called conceptual blending. Okay, so and the project kind of is kind of build. It's going to try to build a kind of general set of software tools that implement this model, this kind of blending engine, and they're applying that to various things like common sense, conceptual blending, so taking ideas like of house and boat and coming up with the idea of a houseboat, but also kind of digging deeper into some domains, particularly mathematics and music. So we're 2 years into the project. There's a lot of work going on, so there's a bunch of papers at ICCC this year if you're interested in finding out more about that. But, you know, maths, music, it's all very worthy. What about games, right? That's what we really want to do. We want to generate games. So we thought, why not apply, Joe and I thought, why not apply these ideas to game generation. And this is kind of like, on face value, is kind of quite an appealing idea. Kind of taking two existing ideas and mashing them together is a kind of common pattern you kind of find in game designers talk in this way. And this is a subreddit called Game Ideas where people post. They post a whole bunch of ideas about games they're never going to build, so they want other people to build them, and then people say it's a rubbish idea, it's a fantastic idea. And here there's I've searched for the keyword meets, you probably guessed, right? So this is a common way of expressing that somebody wants to make, GTA meets Call of Duty meets Need for Speed. Wow, that's going to be an awesome game. Right? So on face value, taking existing ideas and mashing them together, we might be able to get something interesting out of that. And Mark just very helpfully tweeted a reference to a paper by, I think it was, yeah. Yeah. So that's an interesting paper, which I'm hoping to look at after this talk, which is about how game designers can use the idea of conceptual blending. So, there's kind of traction to this idea, hopefully. So what we're going to do is we're going to take this general model of conceptual blending that the co-invent project is putting forward and trying to realize in a set of software tools, and see how that plays out in the context of game design. Right? So the way I'm presenting it here, we can think of it as 6 kind of phases of a blending process. Right? So the first phase is to take 2 games. All right, so where these games come from, we're not going to really dig in too deeply into that. That's a whole other question. But we've got these 2 games, and we want to have some way of mashing them together. So the way this works is, first step is you kind of find some common structure in these 2 games. And that shared structure can be thought of as a kind of third game concept, which is more general than the other 2. So there's kind of idea of a general games concept which could be refined to either A or B, right? And typically that's, when I say generic game, when I'm sort of talking about games here, these are kind of more like fragments of games. It's not a complete game idea, it's just the idea that maybe this entity and this entity exist and they interact in a certain way. So these are kind of really fragments. So we could take that very general concept and we could add more entities and more rules and eventually end up with B or A. So given that common structure, we can blend the 2 together by identifying the things which are called common and which are identified as common in the generic game. We can identify those as the same thing in this 4th game, and then also add in the other stuff that's unique to A and B, and we come up with this kind of blend, which is going to combine those two game concepts around some kind of shared structure. Now, hopefully, that's going to be an awesome game, but it's probably not going to be an awesome game. You're just randomly mashing these 2 ideas together. So we now do some evaluation, right? So how does this actually work as a game? I'll talk more about that in a bit. It's probably going to be rubbish, so we have to backtrack a bit and go, okay, well, we don't want to blend B and A. That doesn't work out when we just think about this common structure we've identified. Instead, we're going to kind of think of 2 other games, A prime and B prime, where we throw away a bit of the structure from A and B, right? So these are slightly more general versions, perhaps, of A and B, where we've removed the bits which don't work out when you bring them together, right? So this is called the weakening process. So we're kind of backtracking a bit on A and B and saying, okay, let's throw some stuff away. And then hopefully, when we blend those 2 together, we will get something which, when we then evaluate it, is going to pass muster, be something playable and interesting, and then the kind of final stage, which co-invent talks about, is the idea of running with the blend. So once you've got these A prime and B prime blended together in a new game, there's kind of new opportunities to develop the game structure a bit more, or the general conceptual structure. So there's the idea of elaborating or running with a blender. So it's important to say, so this is the kind of co-invent, very much the co-invent model. They're building a set of software. We're building a set of software tools to implement this in various domains. And what I'm talking about here is not an actual system, right? So this is an idea for a game generation system. So if you have one takeaway from this talk, it's that we don't actually have any working code, right? Okay, it's very important. But, so without any working code, what are we going to do? Well, what we do in the paper is we take an example and work through that in detail, right? So we're imagining how this system, which we're hoping to build, is actually going to do this in practice, so computationally. All right, so what we did is we took 2 games. We thought, OK, let's just smash these together. All right, so what happens if you get Zelda and Frogger and blend those together? And that's what I'm going to answer. I'm going to give you one possible answer anyway in this talk. OK, so thinking about 2 game designs, what are we actually blending together here? So what are the concepts that are actually being combined? Well, the way we address that question is thinking about what's called VGDL, Video Game Description Language, and this is a language that's been developed to describe simple 2D games. And it's been used in general game playing research with a lot of success, and it's increasingly being used in procedural content generation. So Julian Tagilius has done some work in it recently. So instead of taking the full Zelda and Frogger games, what we're going to do is take very extremely cut down versions of them in VGDL and see if we can take those descriptions and think how we can blend them together. All right, so what do we get when we cross these very, very cut down versions? So if you're looking at, so this is what VGDL looks like. So this is a description this is the entire description of the Zelda game in VGDL. This is available. This is exactly the same thing which was in the general game playing competition library. And we pretty much chose, there's a library you can get online as referenced in the paper. We just pretty much chose 2 examples fairly randomly from those games that looked fairly simple. And we thought, well, they might blend well together. And we kind of worked through it. OK, so what you get in VGDL is you basically got kind of a specification with 4 components. So there's a set of sprites and kind of entities that can exist in the game, an interaction set which describes how those entities actually interact with each other, a termination set which gives you conditions for either winning or losing, and then a level mapping which just allows you to give describe levels in terms of an ASCII format. So there's a mapping which you then say give an example level. And that. So let's try and dig a bit deeper into this because we're going to have to think about what we actually do with this VGDL structure. So I'll explain, hopefully not too long with the detail, a little bit about how Zelda works. This is kind of a set of entities, right? So this is a sprite set for Zelda. So these are things that exist in the game. So we've got a door, we've got an exit, we've got a sword, we've got a key and walls. And some of these entities, these sprites, have kind of relationship with each other. So there's a kind of hierarchy here. So you inherit properties down the hierarchy, right? So probably can't see in all of these, but there's some properties attached to these things. So for example, we've got movable characters, and then Link is a particular kind of movable character who is a shoot avatar. So that's a key word which tells VGDL, describes exactly how Link should move around. Right, so we've also got monsters, and there's various kind of keywords you can use to specify the behavior of the monster. In this case, it's a random NPC, it just wanders around. Okay, so we've got Link. He can pick up a key, so he can change state from no key to with key. We've got various kind of monsters that move around different speeds. We've got a movable structure. We've got a key which just stays where it is until it's picked up, and walls which don't do anything. And then we've got a sword which also describes a certain kind of form of combat. Okay, and then we've got the exit as well. It's very important. So here I've also added the termination conditions. So this is when this reaches 0, then something happens. So in the case of when you have no links left, then he's died, you lose the game. If you've got no exits left because you reached the exit, then you've won the game. Okay. So that's the kind of basic entities in the game, and then we've got some rules to describe how those entities interact with each other. So this is the complete rule set for the VGDL Zelda. And I won't go into too much detail, but you've got some kind of general things like things which can move. If they hit a wall, they've got to move back, so they can't go through a wall. Some basic rules for combat, whereas you hit a monster with a sword, it dies. But if Link interacts with a monster, then he dies. And then the kind of all the gameplay is in this version of Zelda really is that you've got to pick up a key and then go to the door. Right? So these set of rules handle that. Is that if Link's in green, if he hasn't got a key, he can't go to the exit, he just steps back. If he hits the key, then he transforms into the with key state. If the key is hit by Link, then the key disappears. And if you reach the exit, if Link hits the exit, then it disappears. Remember, the win condition was there were 0 exits. So this is the rule which wins you the game. Okay. So I won't go through Frogger. There's the description, a whole bunch of entities, and a whole bunch of rules, which I won't go. It's described in more detail in the paper. Okay, so how are we going to take these two descriptions and apply blending? So if you remember, go back to the general model I described at the beginning. Remember, the first step was this identification of common structure, right? A generalization step. So in this case, this is entirely, there's not much principle behind this. This is the kind of an obvious mapping that Joe and I came up with. So there's some kind of obvious things like certain entities in both games use the same keywords. They have the same properties, basically. So home and exits are doors, right? Walls are actually called the same thing, so perhaps that's something you could use syntactic measures to map them to each other, but they're both immovable. So, but then keys are also immovable. So do you want to map walls to keys? Probably not. Okay. And then in cases like, monsters, they're both kind of NPCs, so there's a reason to map those together, perhaps. And then the two avatars, that's an obvious case of why you might want to map those together. You could consider kind of crazier mappings where, say, the player in one game was mapped to an enemy in another. You know, there's obviously a huge space of possibilities here, but we think so in the initial system we're planning, it's going to be kind of quite cut down and obvious how this is done, but still lots of choices. Okay, so given these, we can map these together, and we can build a generic game concept which has these general entities which are mapped to each other. So we've got an avatar, we've got an enemy, a wall, and a goal. All right, so then we have a blending process where we then say, well, there's a game which identifies where the home in one game is going to be the exit in the other. Let's call that exit. Let's call this wall, obviously. But then we've got some choices to make when we blend together the avatars and the enemies. So in the case of the avatars, we're identifying Link with the frog. There's a choice to be made there. Do we want to shoot avatar? The shoot avatar is something that can use a sword. The move avatar can just move around, do nothing else. So let's pick, in this case, we're going to pick shoot avatar. And then we've got the Zelda monsters which wander around versus the trucks in Frogger, which just go left and right. So we're going to pick the missile, right? The thing that just goes left and right. So we're going to kind of throw some information away. So this is an example of what I call weakening, right? We're actually not now blending the full games. We're chucking some structure out of both games in order to get a successful blend. Okay, and there's a whole bunch of other entities which you can all just throw into the mix as well. So these end up all these entities from both games end up in the blend of things. So you've still got the logs, you've still got the water, and the sword. Okay, so given that kind of, we've thrown everything in the pot together, we can now take all the rules from both games and throw them all into the pot as well, except now some rules work on common objects, right? Because we've identified, say, frog and Link. So we now get some interesting effects where there's kind of rules to kind of do similar things, and we don't want them to necessarily. So in this case, we've got two rules where the first one comes from Zelda. It says that movable things can't move through walls. And then from Frogger, we know that the avatar also can't move through walls. Okay, that seems fine. One's a more general example, one's a more specific. Unfortunately, the implication of our generalization step was that now that trucks can't move through walls. And that's going to be a problem because in the Frogger game, we had the trucks being spawned and coming across and then hitting a wall and, hitting the edge of the screen and dying. Now we're going to be hitting the walls and basically having this massive pile-up, right? So there's going to be like all these trucks, which, you know, it's not going to really spoil the gameplay, but it's not going to look have this horrible pile-up. So we're going to have to do some playing of the game. We have to simulate the game in some way and identify this problem with this rule, and then trace it back to the fact that this is happening, which is caused by this, and then decide, actually, we don't want that. It's another example of interactions which end up in the blend. So, too far there. So we've got this example where if the link goes to the exit, then the exit disappears. That comes from Frogger. And the rule from Zelda, of course, was you have to have the key before we go to the exit. Now, this means that the more general rule means that you can just go straight to the exit without picking up the key. That's going to make the game very easy. So we'll probably play this out and then decide that, in fact, we don't want that as well. OK, so skipping over a lot of detail, what we end up with is something that looks like this, a game called Frolder, where we've taken elements of both games, mashed them together, right? So here we've got Link. This is terrible graphics, but here we've got Link down here. Oh yeah, we've got monsters wandering back and forth like cars, like trucks on a road. We've got little Link. He has to cross the road, get the key, and then cross the road back down and go to the exit. And also he gets to fight the monsters whilst he's crossing the road, which is also something you might want to take out of the game because it might make it too easy. I should also kind of cheated with this example as well, because what I've done is I've put the key the other side of the road to make it interesting, but the key can go anywhere, so that raises questions about where the level design is coming from, right? So we've merged the game rules, but we probably want to merge the levels in some meaningful way as well. Okay, so just to recap, there's a whole bunch of design choices that we've kind of imagined this computational system's going to have to kind of tackle. Things like selection games and running with the idea once the blender's been constructed. We really don't have much of a handle on how that's going to work at all, and we imagine it could be some part of some kind of wider system. What we're focusing on immediately is getting a system which just does this kind of basic blending and checks for validity in some way, and then we need to think about how we can tackle things like creating simple games and things which are playable. Okay, so that's what I've just said. A couple of other things that come up in future work. So there's a lot of work going on around VGDL now, but the tools out there for it aren't that great. So I think there's probably, the community needs to invest in a bit of time and effort working together on some stuff. Like I said, there's kind of looking further into the future work. There's definite issues about how we might blend designs, perhaps by representing them as designers and then blending those designers. And we might look at perhaps audio-visual blending. So imagine once you've blended these two things, you might want to come up with an icon avatar which actually represented them, some kind of blend. Okay, thanks very much. Any questions?
So a lot of time with analogical reasoning mapping, folks used relationships between concepts instead of attributes about the concepts themselves. Is there a reason that you chose to use sort of concept to concept?
Just because that's kind of the affordance of VGL, I guess, would be the answer. So no. So you might be able to map particular interactions onto each other would be another approach. Yeah, I think that's what you're getting at, right? So that would be another level where you're actually looking at an entity in terms of the interactions it underwent and drawing parallels between them there. Yeah, that would be interesting, certainly. Yeah.
On that, sort of I mentioned this yesterday. It's a hammer or drum I keep beating, but there's like work like I suggest looking at Charles Kemp's like infinite relational model, which can look at well, any number of tuple relationship, but there's also a lot of work with dyadic relationships of doing sort of automatic clustering based off of seeing things that have similar types of relationships, which might help with like lessening the need for like the weakening or something of like, well, we know that these things interact in very similar ways and have also similar like, you know, there's some balance between that they have the same sort of.
Yeah, so that's when constructing that initial generalizations. Yeah, because well, I mean, the way we explored it in the paper, it's very simplistic. So yeah, that sounds like an interesting route.
I don't want to take up time from pizza, but you don't have to blend everything. So you can always do the levels procedurally using the rules that are blended. So when you're saying it's going to be too easy, well, the level will take care of that, right? Because you are just saying like,
yeah, you could have
rule will be too easy. Well, that depends on the context.
Yeah, you certainly can have another kind of module doing some separate level generation using whatever, and yeah, absolutely. Yeah. We don't want to make it too hard for ourselves. Mike.
Someone's asked if Frolda is available online.
No, but it will be shortly. I made that promise now here. Yes.
Yeah, it seems very much like you've like are working towards creating like a ROM check fail like generator kind of thing, where like I think an interesting portion of that is that like yeah, sometimes like if you get a specific movement type and like the sort or something, like maybe it is too easy, but also maybe sometimes it's too hard, and like that's sort of an interesting space.
Yeah, that's.
You don't even necessarily maybe need to worry about. Be like, it'll create.
That's what we're trying to conceive it as something like that exactly, where there's kind of perhaps inspiring and perhaps a bit interactive as well, in order to bypass the problems that's going to be fully automated.
You know, I guess it seems to me that to really work with this approach, you need to have some way of reasoning over the rule systems that emerge from the blending. Because it just sort of seems like a lot of game combinations would end up with something kind of either very trivial or.
Yeah, I think getting bots to play the games and assessing it that way is our kind of that's going to be our strategy. I don't know how far that's going to get us, but. It's difficult to say if there's any kind of intrinsic things we could say about the game designs without actually playing them, I think. Game designers, they play test, so that's probably the way to go.
Kind of bouncing off some of the themes we've been hearing well, one of the things you're very focused on is blending these notions of mechanics, but there's also some meta-level blending you can do, like for instance, Frogger is very arcade. It's single screen. You get to the end of the screen, you get a new level. Whereas Zelda is this large, sprawling world. You are trying to get to the other side of the screen, but you're also trying to explore the space.
Yeah.
And are you planning on having some kind of affordances?
I guess that's a cool idea. We rely on having a much richer representation of the game, and VGL is, purposefully very, very stripped down because it was kind of developed for a different purpose. So I don't know, maybe we should be VGDL2, maybe, I don't know, with that kind of stuff in. Yeah.
So being fully aware that what I suggest will not be implementable in the VGL thing you're saying, I have to point out that game designers don't just do playtests. Game designers also have design patterns and have like higher level plan.
Yeah.
So it's not GTA meets Call of Duty because now you have a gun or whatever. So
I guess good game designers do. Yeah.
Yeah. Well, yes.
Yeah.
Well, not AI game designers for now. But
yeah.
In a sense, VGDL is kind of like some of those design patterns encapsulated already.
Yeah, I mean, there's kind of game fragments. We end up kind of a system which will have lots of kind of parts of games. So there's definite potential there. I don't know. All right. Thank you very much.
Can I grab the microphone? Awesome. It's really great. Like, that was really good. Yeah. There you go. The final glimpse is the pizza's coming in. Thank you so much for tuning in, and we'll see you at the next
event.
That seems.
Oh, we've also ordered for player modeling as well.
Probably not to refer. Although I do think that the idea of